Like I have a project, I have an open source project called Coriander where I take CUDA kernels and then I compile them into OpenCL. Now, this sort of works. A challenge I found was that I didn't feel that I had the right to read the CUDA API docs. So the only way I could learn about the CUDA API was by reading other programs that used CUDA, and therefore, for compatibility purposes, I feel that I have a fair use to look at how they're using the API. But obviously, this is very convoluted and quite hard. So, so I'm avoiding CUDA here. I mean, I nearly chose CUDA, but like AMD HIP. So AMD HIP is basically CUDA API, but all the words CUDA replaced by like HIP in all of the API calls. So it's basically the similar API, but just with slightly different name. It's open source under an MIT license. It's already supported by 12 PyTorch. It's very similar to CUDA. I feel that there's not much risk of being sent to cease and desist by NVIDIA. If they were going to do that, they would already do that to AMD. Even if NVIDIA did that to me, I feel that AMD might help pay for my defense, because if I had to retract mine, then that would be evidence that AMD would have to retract theirs. Alright, so I'm choosing AMD here. It's sort of a compromise decision, but I feel like it's open source. It's already sort of supported by PyTorch, and there's little IP litigation risk, relatively small IP litigation risk, I feel. Alright, ISO choice and design. So using this RISC-V, this is very popular recently. Many projects are using it. It's very nice to use. I'm enjoying using it. I'm using the ZFIX extension so that we unify the float and the integer register file. We might need to break with RISC-V in order to migrate to the BlameFloat 16. Now, there might be an extension already for BlameFloat 16. If there is, that's good. I want to know about that. I haven't found one yet, although I haven't searched incredibly hard, I have to say. But yeah, if you know of an extension. Otherwise, I might have to create my own extension, maybe potentially. But I will probably have to therefore modify the LLVM and all of these things in order to handle the extent. All right, how to handle DDR memory and PCIe link. Right, so I don't want the DDR controller and the PCIe interface to be in very GPU. I feel that these are standard components, and I feel that the appropriate way to handle these is to just drop in some third-party IP. So whoever takes the GPU out, they can get hold of a third-party IP controller for DDR and an interface for PCIe, just drop those into the design. I feel that getting hold of a GPU, that's kind of challenging. Getting hold of a GPU design that's verified, etc., that's kind of challenging. But getting hold of a DDR controller, PCIe interface, I feel there should be some out there. And they could just be dropped into the design. I don't see any point in like bundling those in with the very GPU, so keep those factorized out. As far as how to talk with those, so I'm going to use AXI4 because this is a fairly standard interface in industry. However, it seems like AXI4 is not sufficient to fully specify the interface as far as I can tell, so there's probably still going to be some controller-specific integration somehow. If anyone knows like a standard way of interfacing with DDR memory controller and PCI interface, I would be very interested to know that. As far as I know, there will be some controller-specific integration. Do we need network on a chip? So I'm reliably informed that yes, we do. However, I'm not sure about this. Like, I feel that the GPU is sufficiently hierarchical, and maybe we don't need network on a chip. Right? Like all of the cores, they sit in a compute unit. So the cores communicate with the compute unit communicates with units above that. So I'm not sure that we need the network on a chip. I'm not sure. I'll see, I'll find out. So what's working? So single source compilation works. So you can write some C++ that contains the GPU kernel. You can compile that. That kernel can then be run on the simulated GPU. This all works today. The compilation is using Clang LLVM to split out the GPU kernel from the host-side code and then compile that kernel into RISC-V. We need to provide a runtime library, and I'm providing a HIP-compatible runtime library. The HIP runtime library handles things like virtual memory allocation for the GPU, transferring data to and from the GPU, transferring the kernel to the GPU, and launching the kernel. So this exists today, this works today. A basic GPU core. So we've got a basic GPU core. It's using the RISC-V ISA. It's got ancient FP32 arithmetic. It's got a relatively fast propagation delay, I feel. Things that we need to add in are instruction parallelism. Currently don't have. Caching, we need to add in caching. Currently it's using FP32. We need to migrate to the BrainFlow 16. And there's some floating point operations we need to add, specifically exponential, logarithm, and tanh, maybe a couple of others. Things we don't need or want. We don't want superscalar execution, because this uses absolute tons of data. This is great, because then we don't have to implement superscalar execution. So we don't need to do out of order or micro operations or any of these things. Right? That's gone. So it's relatively simple. We want the GPU core to be relatively simple, because then it takes up a small amount of die area. We're going to have thousands of these on the GPU die, so they all have to be relatively small and simple. But this makes our life easier. GPU controller. So the GPU controller sits on the GPU die, and that communicates with the host side runtime library. It handles copying data between the GPU global memory and host side memory in either direction, sending kernels to the GPU compute unit and launching them. So that's working today. PyTorch to do. So PyTorch is compiled for AMD. Well, it's compiled for CUDA, and you can also compile it for AMD here. When it's compiled for AMD here, the kernels are compiled into the AMD ISA. So those won't run on our GPU, because we've been compiled to the RISC-V ISA. Now, more or less what we just need to do is to recompile PyTorch using our own runtime and libraries. However, we need to create those libraries so that when we compile PyTorch, it will compile into RISC-V. This needs a bit of tweaking and hacking around. I've done something similar, because in my project where I took CUDA kernels and compiled those into OpenCL, it's kind of similar, actually harder, so this is easier than that. It's doable, but it will need a certain amount of time. It's not just like an hour of like typing .fetch-configure or something like that. There will actually need to be some modifications in header files and definitions created and modified and so on in order to do this. But it is doable. Alright, so verification. So if we want people to take this out, spend millions of dollars on it, potentially hundreds of millions of dollars, we need to show that it's going to work. Right? It's not enough to sweat the code and say, well, I guess it worked. We need to prove or make it very certain that if it's taped out, it's actually going to run. In industry, 80% of development effort / money / time goes into verification, not into writing the code. I'm creating unit tests as I go along. They all run currently in Nicholas Verilog, and then some of these have been ported to Verilog. I'm sort of porting more and more as I go. One of the biggest challenges I've faced so far is uninitialized X values. These are quite hard to detect, I find. One way to detect them is to use gate level simulation with iVerilog. This catches quite a few, but not all. I also experimented with using like asserts with iVerilog. That also catches some, but again, not all. There's many edge cases and point cases. What I'm finding works quite reliably is random initialization with Verilator. So Verilator can, whenever there's some new wire created, you can tell it, or I just initialize it with a random value. So sometimes it will do it, sometimes it will not. If you run it enough times with the random initialization, a failure to initialize will manifest in a failing unit. These failures can be hard to track down, but at least we know there's a bug to fix. I feel it's vastly preferable to know there's a bug somewhere and to have to spend some time tracking that down compared to not knowing there's a bug at all. And if we run the test many times and we don't manifest any bugs, then we can be reasonably confident that the initializations are working okay. Not entirely 100%, because there's sort of like probabilistic element here, but I feel that it works fairly well. Alright, so unit test and initialization. Alright, performance. So there are three measures of performance that we care about. One is propagation delay, one is die area, and one is cycle count. So propagation delay is the time for at each clock cycle, any changes in flip-flops inputs has to propagate through our combinatorial logic, and that takes a certain amount of time, which is the propagation delay. The propagation delay controls how fast we can set our clock speed. So the faster the propagation delay, the higher the clock speed we can use, and the faster we can run our GPU. The cycle count is the number of cycles to run a particular instruction. So the cycle count combined with the propagation delay basically decides how fast our GPU is going to run. And then die area factorizes into cost. Like the the more die area, the higher the cost of taking out, and the lower the yield. So the smaller the die area, yield goes up, cost of taking out goes down, so overall cost goes down. For the propagation delay and the die area, so I believe that you can use the OpenStar/timer to do this. However, I wasn't able to figure out how to get that working. I sort of tried, but I didn't figure it out. What I'm doing is I'm using YoSys to synthesize down to a gate level netlist. I'm not doing layout here. I'm using the structure of the logic gates, like the network of logic gates, as a proxy for how much time will be in the propagation delay and the die area. But this doesn't take into account things like wire length and layout. So it's just a proxy. To actually get the actual exact propagation delay and die area, I would need to run layout, which I'm currently not doing, but will obviously do in the future. So I'm using YoSys to synthesize down to a gate level netlist. I'm using an open source 90 nanometer cell library called SAD EDK90 to do this. This is provided by Synopsys, which is very nice of them. But yeah, it's open source, it's not IP encumbered, so we can freely use that. And then what I'm doing is I have a custom script that walks the netlist. And what I'm doing is I'm calculating propagation delay in units of NAND gate propagation delay. Right, so what is NAND gate propagation delay? It's the propagation delay of a single NAND gate. So if we have one NAND gate, then the NAND gate propagation delay is 1. If we have two NAND gates, one after the other, then it's 2. If we had a NAND gate followed by a NOT gate, so a NOT gate propagation delay is about 0.6 times a NAND gate propagation delay. So a NAND followed by a NOT is about 1.6 NAND gate propagation delay. And this should be fairly node technology independent, like whether we're using 5 nanometer or 90 nanometer, a NOT gate is about 0.6 the propagation delay of a NAND gate. Not exactly, but approximately ballpark. So basically, like calculations like NAND gate propagation delay is, I feel a fairly reasonable proxy to be able to judge, okay, this implementation is faster than this. I don't know the exact propagation delay, and depending on layout, like actually the relative rankings might not be quite the same, but hopefully it's a reasonable proxy to be able to choose a faster circuit over a slower circuit. And similarly, the die area I calculate in terms of NAND gate die area. So we've got 2 NAND gates, that's 2 NAND gate die area. So again, we're not doing layout, we're not taking into account wires, and we're not taking into account like power lines. Okay, but I feel it might be a reasonable proxy in order to get some indication of propagation delay and die area. And then cycle count is easy to measure, it's just the number of clock cycles for particular test programs. So we run a test program like, say, matrix multiplication, and how many clock cycles does that take? Alright, so this is performance. So all of these like tests run on a CI server using Circle CI, which is free for open source projects. Basically every commit, it calculates the measures the propagation delay, the die area, and the cycle count, as well as running the unit test for the verification. We actually have like integration tests and stuff too. Alright, what open source tooling am I using? So I'm using Icarus Verilog, which is a simulator, Verilator, which is another simulator, and YoSys, which is a synthesizer. So what are the good and bad points about these? So Icarus Verilog it's very easy to use. It generates compiles code very quickly, and you can write test cases in Verilog, which is super nice. The bad points is it has limited support for System Verilog. So I built it original a while ago, and it hasn't been updated much for System Verilog. It's got a strict GPL-v2 license now. This is not an issue if we're only using Verilog. However, I want to be running simulations from PyTorch, from C++, which means I need to link my C++ code or the PyTorch code to the iVerilog library. If we need to link those together and the library is GPL-v2, that means my code needs to be GPL-v2 too. I want my code to be under a more open license of MIT, so I want to avoid linking with the GPL-v2 iVerilog library. It's also unclear to me how to guarantee detection of initialization errors when we're using iVerilog. Now moving on to Verilator. Good points in Verilator, it's got a really great reputation in the industry. It runs quickly. Now I say it runs quickly. It compiles and generates relatively slowly, but once it's compiled and generated, it runs quickly. We've got a relatively unrestricted license, the lesser GPL-v2, so we can freely link to old GPL-v2 code without our code needing itself to be LGPL2. So this is great for VPI linking with C++. I find that it detects initialization errors reliably using the random initialization. Easy to link with C++, which is great for when we're running like PyTorch against our simulated GPU, and system Verilog support is underway. Bad points. So the system Verilog support is still in progress. Compilation generation is fairly slow, and it's hard to figure out. You have to set up some files, a whole bunch of code in order to run anything at all, compared to iVerilog where you can just run it on the command and it's super easy. And you can't create standard Verilog test bench unit tests. Now, you can kind of hack around your Verilog so that most of your testing IP is in Verilog, and then the C++ is just a very thin shell on top of that. However, you end up with the resulting Verilog code is not as intuitive to understand and to read and to maintain as if the whole thing is written in Verilog. That said, because of the advantages of Verilog as a relatively unrestricted license and the detection of the initialization errors, I'm gradually moving my tests into Verilog and moving into Verilog. And then Yosis is the synthesizer. So Yosis is really amazing synthesizer. Like, it's awesome. I haven't discovered a bug in it yet. Right? Sometimes I find that bug and I'm like, oh, I found a bug in Yosis, but it's always a bug in my own code. Always something I've done wrong in my own code. So yeah, Yosis just works really well. It's very reliable. It can handle a very diverse space of Verilog code. It doesn't handle system Verilog, so you have to feed it Verilog. But if you feed it Verilog, it can handle like a diverse space of Verilog. If it can't handle something, it will say, oh, I can't handle that. It won't just give you the wrong answer. So either it will give you the right answer, which is the vast majority of the time, or it will say, oh, I can't handle that input, you need to change something. And it will tell you approximately what you need to change. Bad points, as for all of these tools, limited support for system Verilog. Right, now there's some tooling I tried, but I haven't used yet. So one is OpenStar Timer, one is SC2B, and one is Kubeflow. So OpenStar Timer, like, as far as I know, it can be used to measure the propagation delay. It might also handle layout, I'm not sure. Anyway, I couldn't get it to work. Maybe I'm using it wrongly, but I couldn't get it to work for myself. So yeah, so I'm not using that currently, but maybe in the future. SV2B. So SV2B is a very nice project. It takes system Verilog and it converts it into Verilog. So then we can then feed that Verilog into all these other tools that only support Verilog. So the good point is it works with system Verilog. Bad points is when something goes wrong, it dumps you into the generated Verilog. So when I have an error, I get dumped into generated code that I didn't write. So I have two sets of code. The system Verilog that I wrote and know intimately and understand very well, and then whenever I get an error, I get dumped into code I didn't write and that's generated, which is quite challenging. I sort of tried that for a while, but personally, currently, I find it more effort to deal with the dual code than to simply write everything in Verilog, keep everything in Verilog, the sort of lowest common denominator across all the tools I'm using. But I do like the idea of SV2B. I feel it would be nice if it would be really nice if SV2B could do what it does and then somehow dump you into the system Verilog when there's an error, along with a system Verilog related error, rather than dumping into the generated Verilog. Maybe. Kubeflow. So Kubeflow is a layout software. As far as I know, it's the only open source layout tool. Although it may be OpenStar Timer has a layout too, I'm not sure. Bad points, I found it hard to use. I tried it with like a very simple example, like one NAND gate or something like that, and I couldn't get it to work. So I'm probably just using it wrongly. But yeah, like I'm not using it currently. I will probably use it in the future and figure out how to use it because basically, as far as I know, it's the only open source layout tool. So gaps and opportunities for open source. So system Verilog support. So I need a DDR5-6 controller and a PCI interface. A BNAND block generator. So as far as I know, all BNAND block generators are all provided by Foundry. Now I'm wondering if there's a way that we could have like an open source BNAND block generator, which is somehow Foundry independent. I don't know if this is possible, but like we have like these languages that support creating like logic gates that become like logic cells, which then get changed into the Foundry stuff. I wonder if we can do something similar for BNAND block generator. I don't know, I'm just kind of throwing it out there. And an easy to run chip layout generator. Right, so system Verilog support, this could be adding support to existing tools. It could be tweaking SV2Bs at the workflow stage within the system Verilog code. DDR5 and 6 controller. So ideally with a full verification suite. So when someone takes out the chip, they don't want to just take a DDR controller that has just been developed a bit, and there's no guarantee that's going to work, because the 80% of development effort for ASICs is on verification. So if they have to write the verification themselves, that's 80% of the development, so that's a significant burden and a significant obstacle. So it does need to have a full verification suite. We want to have as standard interface as possible, e.g. using AXI4, and ideally we should have some kind of proxy module for running simulation. So we shouldn't have to run the full DDR controller PCI interface when we're just running simulations. We should be able to bypass that for simulations, at least for when we're simulating a whole end-to-end system. VLAN clock generator, is this possible in open source? I don't know, but I'm just kind of throwing that out there, is there a way to do this? Easy to run chip layout generator. So this might be as simple as adding documentation to Qflow, but I think there might be need for some test cases though, because I hit issues very quickly and easily, but I might be just using it wrongly. Alright, so thank you for listening. Very GPU aims to be an open source GPU ASIC dedicated to machine learning. It's got an extensive verification suite, like unit tests, integration tests, etc. We're calculating performance metrics for die area, propagation delay, and cycle count. And it's dedicated to machine learning. So we intend to use only brain 16 in order to keep the die area low and yield high. We intend to implement only floating point operations needed by ML, and we intend to ensure that it works with PyTorch. Cool, thank you for listening.
Hi, Hugh, are you still with us? Hello?
Yeah, I'm still here, yeah.
Sorry, because we're having some problems here, so I was very afraid that you are disconnected from us. Okay, so do anyone here have any questions? 在场的各位不知道有没有什么问题有关于 OpenGPU 的部分想要询问的 Okay, so maybe we need to give them some time to think about what they want to ask, but I have a question I want to ask with you, that comparing to your work, there are plenty of open source GPU implementations regarding the GPU, one such as the MIAOW, the MEOW, I believe it's from some university in America, and there is a NUZI, the NYUZI, which is inspired by the failed Intel Level B, I believe. So, what is the design comparison between theirs and yours? Because apparently your design is based on RISC-V instruction set architecture instead of the existing and proven ones. So, this is my question, and please, if you allow me to, yeah, sorry.
Yeah, I'm not very familiar with the other open source GPU out there. There's one called Vortex, which I believe is targeting FPGAs, and I'm not familiar with the other one that you mentioned.
I see. Okay. So, I have another question that's kind of straight away as well, but I'm really curious about that. Back in maybe 1 year or 2 years ago, there is another group of people who would like to develop their own GPU based on the RISC-V instructions, RISC-V ISA. So, but they chose to use the open power instead in the end. So, may I ask why do you want to use RISC-V ISA as your base? I know this is very new, it's very cool, but what is your concern here?
The question is why I'm using RISC-V rather than some other ISA?
Yeah.
It just seems like a natural ISA to use. It's out there as open source and lots of projects using it. And I haven't come across any major issues with using it so far. The main issue that I will come across is the fact that I haven't found an extension for VM16 for the RISC-V. But it seems like it's got a lot of tooling support in general. So what other ISAs would you think might be a good fit instead of RISC-V?
Well, I'm not very sure, but some people are actually implementing their own GPU based on, I believe it's ARM-based, which is some kind of risky because the ARM won't be happy that you're trying to re-implement their ISIS, but I know there are some groundworks there. But yeah, that's some kind of the try. Anyways, so yeah, here we have questions here. Please come here because the camera feed is here. Yeah, 进来这边，然后麦克风这边。
Hi, thanks you for your presentation. It is pretty significant that your GPU support the PyTorch framework, and I'm a bit interested that since we have since PyTorch is a large framework and it incorporates with Python, and we also have something like Anix or a more static model that doesn't require a lot of framework or a lot of layer on top of that. Yeah, and it also describes the whole AI model. Yeah, so yeah, since you are targeting in machine learning, so if you ever considering or yeah, I would like to ask what is the benefit to support the whole PyTorch layer instead of just Onyx or any static model format? Yeah.
Yeah. So here's the problem, and yeah.
Yeah.
So the question is, why am I targeting PyTorch rather than Onyx?
Yeah.
Is that the question?
Yeah,
I guess I haven't thought about that question.
okay.
So maybe this is a kind of profound questions that maybe you can think about it and then maybe give us a reply in 1 day or 2 or you know in any time you would like to do that. Sorry that because there are many kind of DLAs here in Taiwan that and many DLA makers trying to do their own works, but just like the person here that many of them are targeting the static models instead of the PyTorch or you know the TF Lite because it tries the interpreter. Sorry. So yeah, this some kind of. But anyways, this is open source. You can try to use it and try to do your own work based on it. Okay.
Yeah, I mean, I guess the Onyx is for inference, right? Whereas I'm targeting training. So is that maybe the difference?
I see. So basically, the OpenGPU or the beverage GPU here is targeting the you know but on the H training, and that's the way that yeah.
Thank you.
Thank you.
Yeah, I feel there's a lot of work for inference, but for training, I think that's the reason. Yeah.
I see. Thank you. Thank you. Do we have any questions here? If not, I still have a question here. Hugh, so I'm curious that you're using Verilator for the this emulation, but how is the speed that you're experiencing? Because Verilator is, if I remember correctly, they're adding the multi-thread support for the emulation, but it's very buggy from my experience. So did you use the multi-thread emulation, or did you just use the single-thread emulation model?
Currently, I'm just using the single-threaded and not yet using the multi-threaded. I haven't tried multi-threaded yet.
Okay, I see. Because,
maybe in the future.
Okay, I see. Just one moment. I'm gonna speak in Mandarin to ask some people around here. 戴总，你有没有什么 Verilator 问题想问一问？反正你接下一场就是要讲 Verilator 啊。有什么觉得有趣的？真的不要吗？
那他平常知道 SVA 吗 ？Verilator SVA， 他用的感觉怎么样？
你说 SVA 吗？
对 SVA。
Sorry, Hugh, that a person here that is actually our next speaker will be presenting his own experience on the Verilator, and he's quite curious about your experience on using. 戴总，你说 SVA 吗？对。The SVA in the Verilator. So I'm not very familiar with that, but he mentions about it, and he wondered how's your experience on the SVA in the Verilator.
Sorry, I don't remember what is SVA. Can you remind me what is SVA?
Okay, I will ask him. Hello, SVA 是什么东西啊
System Verilog Assertion。
Okay, it is the system Verilog assertion. Okay, so system Verilog assertion.
I'm just using the normal Verilog assertion using assertions on the C++ side. I'm not sure if that answers the question or not.
Okay, thanks a lot for the answering. And just one more, I'm very curious about that. Do anyone fund you to actually take it out? And there's a chips bill that is passed in America. So I'm wondering that will you be interested in using the 19 nanometer process node or 130 nanometers process node from Skywalker to tape out your the very GPU?
I haven't targeted finding funding yet. I think that's something for the future. Like once I've got more of a, once it's more fleshed out and ready for taping out, then I will look into taping out and finding funding at that point, but not yet.
I see. Well, your talk is actually kind of repo here in Taiwan, so I will definitely forward some interested parties to you, and we will be looking forward to it. And it's about time, so thank you very much for joining us, and sorry for waking you up so late in the United States. And bye bye. Thank you.
Thank you for listening.
接下来是你嘛，对不对？你要去上厕，你要去休息一下。那我们我看一下时间，不好意思，我 lost track of time 还有5分钟嘛，对不对？我们是吗？11点半嘛，对，5分钟嘛。你要用你的那个吗？
对啊，对啊，他什么号都可以接。
好，可以。发个 email 过来，然后我们再就是因为我现在手上有是他的那个我 device 都绑在上面，让我分析。
我记得妈妈还是
只是因为
你再跟他联络，对，然后大家都签好，然后你会后发 email 给我那个录音栏这样就那个卢广仲卢英文的英栏上面一个50栏的栏，对不对？我每次都念的。没事。我在 Facebook 上就是刚刚讲的，就是然后对。他的粉丝，我就跟他联络。好，没事。多了去。今麦几点？
这边有麦克风。
麦在这边，麦控在这边。喂。还有3分钟。
哎呀，讲中文啊？
讲中文吗？好啊。英文很烂，怎么在那个现在这些人，也是台湾护国神山呢？英文太烂，也太谦虚吧 ？CJ 也是英文很糟的呢。CJ 现在还好吧？他现在就老师现在。就蔡纯仁啊，现在还
有点重返荣耀，就是
重返荣耀，
就 IC 设计太红，所以一堆人来。
我其实有想要回去找蔡纯仁吃饭，可是他就讲说他现在疫情他也不太敢出来，可能等年末或明年这样，对吧？到时候你们玩家实验室还有在去吗？
最近比较少。
好，如果以后，但还是要问你们老板愿不愿意，就应该你要问老师愿不愿意啊。不过如果他可以接受的话，我有点想去。跟他拜会一下，对。喂，
手料。
剩1分钟了，开场好了，对不对？
是我自己开。
你自己开，你自己开。
哦，然后我叫戴周，然后其实我原本是个资工系学生，后来跑去瑞昱做 RTL designer， 然后这有点算是我平常休闲的兴趣吧。对，然后过去2年我们在 FOSS-enabled 就是这个议程轨，我们讲了很多开源硬体的流程跟 project 嘛，像刚刚有一堆 Open GPU 的介绍，然后去年有讲过那个一些 XT Pro 这样啊，但是如果你现在真的很想要自己直接投入这个领域，那是我们自己的第一步，就是我们今天的主题就是 Relator。然后这是我 outline， 我会大概讲一下 Relator 这个好用的工具，还有它的局限性。然后就它其实就是一根钓竿，然后看你可以钓什么，然后底下就讲2个然后我们的范例这样。然后我们稍微 review 一下IC Design Flow， 这个是从一个叫阿嬷也懂的 IC Design Flow 那边借过来的，你各位可以上去 YouTube 上去找他的讲解。好，然后这个是过度简化流程，就是如果你直接照这5个步骤做，应该会浪费沙子这样。好，然后首先第一步是，我应该开个色。好，第一步就是 spec 嘛，例如说我们要准备像 RISC-V spec 这个东西，然后接下来你就喂给工程师喝咖啡，他就帮你转成 RTL code 的，例如说就是你的 micro architecture。这个阶段我们通常会写 code 会有点类似 A 等于 A 加 B 这种，又称为 Verilog behavior model 的那种层级。然后这个阶段通常会验证你的function有没有对嘛。然后最常用的方法就是 simulation， 当然还有其他的招式，那我们这边就先不提。然后你验证你功能都对之后，就要做合成。合成完之后就会合出 gate level list， 就是把那些 A 等于 A 加 B mapping 成逻辑闸，然后再做 gate simulation 确定你合的有没有正确或错误这样。然后最后就是进入 APR 的流程，就 place and route， 然后我们俗称 APR。对，然后做完之后就做 post simulation， 然后产生 GDS2 给台积电生产这样。但是如果我们现在要走一个全开源的流程，大概要怎么做呢？首先我们在 simulation 部分就有2个选项，其实前面一位讲者有稍微提过，就是 Relator 跟 iVerilog。然后后段的话就是去年有人讲过，就是 OpenLab， 就是可以一步到底全部走完，这样。然后我们再细看一下 pre-simulation 这个阶段，就是一般来说我们常用的商用 tool 就是那3大家公司出的嘛，那3大家 EDA company 出的 tool。然后这些都是闭源的，而且要钱的。如果你要用一些闭源但是可能稍微免费的话，例如说赛灵思 Vivado， 现在叫 VT， 它有提供 Webpack license， 就是可以去免费的让你去模拟，但是我觉得它局限性都在哪里这样。然后像其他像 Intel Quartz 那边也有之类的工具。Open source 的话就是我们刚刚提到 iVerilog 跟 Relator。然后简介一下 Relator。它目前号称最快的 Verilog 跟 Verilog 的 simulator， 但你讲它叫 simulator 很不正确，它应该叫 compiler。它实际上就是把 Verilog 跟 Verilog compile 成C 跟 C++ 或是 C 正 C， 然后接下来再跟你自己写的 test bench 用 C 加写 test bench 一起编成你的 simulator。然后它目前 license 是 Open GPL LGPL v3， 就是比较宽松版本，就是你喂进去给它吃的东西还是属于你的。然后另外它有一个 license 叫做 Pro Artistic License， 就是它卷出来的东西也是你的。但是 Relator 有一个要注意的地方，就是它不只是个 compiler， 它也是一个类似 library 的东西，就是它有一些黑的。那黑的如果你把它包进你的 project 里，那就会受到 LGPL 的约束这样。然后它目前已经有25年的历史。主要做只是 Wilson Snyder， 还有几十位很活跃的开发者跟上百位的contributor 这样。它目前被 Linux Foundation 底下的 Alliance 去类似让这个社群更加繁荣。所以自从加入之后，它的commit数量我这边没有图，你可以去它的社群看，它的commit数量是大幅成长。然后再来就是因为 RISC-V 现在很红嘛，很多开源的 project。都用 Relator， 基本上你所有路上看到 RISC-V Open Source 的 project 都有提供 Relator 这个 solution。然后它在业界也很常被使用，像这是 Relator 官网上写的，让 Intel、AMD 跟特斯拉之类的大公司都有用。 特斯拉的话，其实他在3年前的 Hot Chips 大会上有讲过，他们使用这个 Variator 去开发他们 FSD 晶片的经验。各位有兴趣可以去找找看。然后学界也很多人在用，像 ETH 就是苏黎世理工大学或是东京大学。国内其实据我所知也不少学校有在用，然后甚至有一些，因为他现在业界有在用嘛，所以有些公司也提供它的 commercial support， 就3-4家这样。然后它的特色的话，主要就是它 simulation 资源就是 Verilog 跟 FOSS-enabled， 然后 FOSS-enabled 不是全部资源，主要局限在可合成的语法部分。详细的话就看打鼓门，因为它有些语法就不支援，所以还是要 check 一下。然后它不只可以模拟，它模拟还可以产生波形给你的 bug。然后再它就是支援 syntax check， 就是 linting 嘛，还有 coding style 的检查，例如说 unused block detection 之类的。然后也支援 FOSS-enabled 的 DPI 跟比较旧的 Verilog 的 DPI 这样，它建议用 DPI。然后再就是 code coverage 的部分，它支援 line coverage、assertion coverage 跟 toggle coverage， 但是不支援arc transition 跟 state。然后它支援简单的 FOSS-enabled assertion， 就是不是完整支援，因为 FOSS-enabled assertion 蛮多很花俏的语法，主要支援就是 stable 或 ROS 这种比较基本的语法这样。然后通常会有一个建议啊，就是你不管是用 Variator 还是用商用 tool 都一样。就是你 SVA 写的越简单越好，你的 performance 才会高。因为 SVA 如果你写的太 expressive、太花俏的话，会拖慢整体的模拟效能。然后它像不 support 的，我查到就是 throughout 跟 until， 当然还有一些其他的。然后最后它有一个很关键的特点，就是它是 cycle-based simulation。它什么 cycle-based simulation 呢？像我们一般ECS 或什么其他 tool 的 simulation， 它看的 evaluation， 它还是看它的。你 Verilog 上面不会写什么 time scale， 你的时间颗粒度是多少，就是以那个为基准。但是 Variator 的话，主要就是以 cycle， 它 cycle 的时间颗粒度通常比你上面的 time scale 好大一点，所以这情况下它的速度就比较快。然后，可是因为这个特性，所以它就不支援那个 delay， 你就 sharp delay 就会直接被无视这样。然后通常的话都只有吃一个 Clark sauce， 当然有一些招式可以让它吃很多 Clark sauce 之类的，后面会提到有个网站有教怎么做这个。然后所以在这个情况下，你把它拿来跑 post simulation 完全没有意义，因为它就不吃 delay， 它也不吃 SDAF format， 所以你为它吃这种 timing information 其实完全没有意义。但是这个特点造就的就是它超级快。它有多快呢？就是按照特斯拉那个演讲的说法，比商用 tool 快了50倍。好，然后接下来我们来看看它的简单的 flow， 就是你现在有一个 counter 点 B 嘛，有没有一个 code？ 然后接下来你用 Variator 把它 compile 成 C++， 还有一些相依的档案这样。接下来你就写一个C+ main function， 就是你的类似 test driver 的东西去 include 它。然后再把它编译一次，变成你的 executable simulator。像这个就是它卷出来的结果，就大概这样，你可以发现有一大堆CPP 的东西。然后像这个黑的，就是你可以拿来 include 的部分。然后它，你另外就是你必须要写一个 main function 去类似初始化你的 Variator 的 context 嘛，然后像上面这边就是那个 Variator 黑的，就是刚刚前面提到他自己有包几个他专属黑的这样，然后后面这段就是环境的建立，例如说你的waveform的 BCD 的那些 file 的建立这样，然后像讯号存取的话，就跟你一般写C++在存取 class 的 member 的方法一样，就是直接叫什么？RO 3之类的，然后所以经过这个流程后，就会编译完之后就跑出你的可执行的模拟器。好，这2页我们就跳过，因为这2页。然后还有一个特点就是，它是一个 two state 的 simulator， 什么意思呢？一般我们Verilog你宣告一个 register， 它有4个 state 嘛，就是0、1、unknown 跟 high impedance。但是 Variator 只支援0跟1，那你会问 unknown 跟 high impedance 跑是哪里的？它就会被 mapping 成0或1。这边0或1是 你可以在模拟期间决定的，例如说，你可以在你编译好后的 simulator 强迫它太零，像我这边是一个32B 的 counter， 所以我太零嘛，所以就全部都零。然后或者是这边是一个32B counter， 全部太零，所以就是一堆 F， 或者是随便给值。你可能会问，我把 unknown 跟 independent 丢掉，那不就行为就错了吗？对，会错，但是因为会错，还代表就是你的 code 应该是有问题的。因为 unknown 跟 high impedance 理论上应该不该被拿来做运算嘛，就是我们会有一个术语叫 unknown propagation， 就是你 unknown 的值一直往后下去做运算，你后面结果就是错的。然后这是你看波形的话就可以用一个图叫 open source 的 GTK web， 然后它是 BCD 跟 FST， 这是两个 variator 都支援的format 这样。然后这是code coverage 的算小 demo 吧，它用的是 Linux Test Project 底下的 LCOP， 就是它会把那个 variator 你执行完后的那个 coverage 的 database 去解析成一个 HTML file 去给你看你的 line coverage 那些东西，这样。然后我觉得这页应该是这个讲题里面最关键的部分，就是一下可以忘记，但是这边记得要记得，对，就是我们会有一个建议，就是 variator 的好处就是它很快嘛，所以你可以用 variator 快速的去提高你的 turnaround time， 就是，例如说你要跑1个小时的 code， 那你可能跑1分钟就可以打到你要的那个 bug， 这样你就可以很快速的 iteration 去提升你的开发效率。但是 variator 也是有缺点，像它有时候会编出怪怪的行为，或者是它有时候会跑爆，对，然后所以这个时候你就需要商用的 tool 去 cover 剩下的部分，所以我们通常会说就是你用 variator 去 cover 98%的那个 bug， 用很快速的方式，但是你用商用的 tool 去 cover 剩下10%，这样的话就是可以大幅提升你的生产力，然后节省你的时间，然后又可以确保你的正确性。然后我们稍微复习一下我们在学校常学到的 RTL verification 的环境，大概就长这样嘛。就是左边蓝色框框是 pattern， 就是用来产生 test case， 然后喂给右边的 DUT， 就是 design under test， 例如说你的 respect code， 然后 test bed 就是用来连接的部分。当你现在你的 DUT 变成 CPU 的话，你就会遇到什么问题呢？例如说你的 memory code 会变成 ASI 或 tile link， 或者是你会支援好多组memory code， 然后再就是你要支援 internal 或 debug code， 然后再就是你的 pattern， 你的 pattern 以 CPU 的话就变成你的编译完的 code 嘛，你要怎么把它拿来喂给你的design under test 呢？然后我们再来看第一个很简单的 case， 然后这个 code 是叫 Akira， 它是交大开发的，目前就是一个经典的 5 stage 的 code 这样，然后它目前可以合成，并在 RT35T 上去跑，然后支援 TCN 跟 DKG、IKG 这几个记忆体，然后它目前是交大的计算微处理器系统原理、原则与实作课程的教材，然后不是微算机器人那堂课，然后课程内容主要就是让学生去改这个 code 的 code， 然后跑上去RTOS 去研究一下 OS 跟CPU 之间的关系这样，然后这边我就不细讲，可以去交大课程网站上去找看这样。然后这是它的 debug 的 block diagram， 然后右边这3个值的部分都是 Science IP， 就是 NIG 这些东西都 Science 的黑盒子这样。然后左上角就是我们的 code，我们要模拟我们的 code 嘛，可是我很懒惰，就是 Science IP 就黑盒子，我就来验它也没什么用，所以我就无视它这样。然后我们的 interface ASI， 不过在内层还有一个更简单的memory access port， 所以我们就直接拿这个来验就好了，就是偷懒这样。然后所以就有右边这3个 code， 就是 IKG 的 iPod， 然后 DKG 的 dpod 跟 IOPod 这样。然后我们的 simple test 就会变成这样，就是我们会白色框框内全部都是 Verilog， 用 Verilog 写的，然后我们旁边造2个假的 run， 就是用来存我们的程式嘛，然后它是一个 to code 假 run， 就是让我们的 code 可以去 exit 它这样。 然后再来就是有一个假的 UART， 就是它行为跟 UART 一样，但是它不会对外 output， 它就只是扣那个 Verilog 的那个 display 去让我们在 console 印出 hello 这样。然后最外框黑色的部分就是我们的 C++ main function， 就是它用来去产生 Variator 要的 character 跟 recess 跟，然后还有就是把程式码把 elf 转成记忆体的那些东西塞到我们假论里面这样。然后这边就介绍一个 Variator 的 language extension 叫做 Variator Public Meta Command。然后它用途就是把你的 register for y 或者是 function 或者 test 变成一个界面在你的 C 加 黑的中。然后其实这个东西真有够方便，还有我一直用这个。就是它长出来的东西就会类似这样，就是我们刚刚上面看到有一个叫 reward 跟 reward 的 function 嘛，然后它就会被 mapping 到这边，就是你可以在 C++ 透过那个 master access 方式去 call 这些 function， 然后做你要的事情。然后我这边的用途是用来就是把资料写到那个假论里面。然后这是 Akia 的 Verilog hierarchy， 就是你可以看到就是 Akia Tetanus 底下这些都是 Verilog core， 它上面这个 top 就是我们 Variator assign 的一个 top 这样，然后这个 top 就是在这边被 assign 的。然后刚刚讲那个 hierarchy 的用途就是，你可以看到我们要 access 我们刚刚 function access 的 hierarchy 跟我们 Verilog hierarchy 是一模一样的，就是 top Akia Tetanus， 然后 mark run， 然后 write back， 就是完全一样，它不会帮你做些什么奇怪的操作，就是很直观。然后再就是这边我们C++ function 这边还有稍微改了一下 respy istar simulator 的 elf file load， 就是让我们把 executable 的 elf file 去 pass 成那个就是记忆体要怎么摆放，然后的资料这样。这是执行结果，就是可以发现我们可以就是很简单的直接去抠去吃我们的 elf file， 然后就印出我们要的 hello 之类的东西。用 C++ 当 test bench 有什么好处呢？第一个好处当然就是 C+ 语法比 C++ 强大太多嘛，你有一大堆 std library 可以用，什么 stack q， 然后 priority q 之类的。然后再来就是它很好 link 其他 library， 比如说刚前面讲 elf file load， 或者是 ncrsys， 就是可以在 console 上印一些有的没的，或者是你就绑一个 instruction simulator 在里面，就你跑一步，然后就去比较一下你的 code 执行有没有正确。然后你绑一些分析的 tool， 还有另一个就是 retry from answer， 就是我们下一个主角。然后就是我们另一个 case， 然后这个 code 叫做 retry sodo， 它是 UC Berkeley Architecture Research 这个 group 开发的。然后他们这也是一个教材，就是 UC Berkeley CH152， 应该是他们的 computer architecture 的教材，好像听说要用3个学期吧。然后它是用驱收3写的，它驱收3，在后期会被转成 Verilog， 然后会给 Variator吃，就可以走我们后面的一般的流程这样。然后它支援1个 stage、2个 stage 到5个 stage， 就是因为这是一个教材，所以就是要让学生去学那个 computer architecture， 所以就这些很多的 config 这样。部分 config 可以在 FPGA 上跑。然后它目前不是一个 standalone 的 project。就是它需要有另一个 project 叫做 ChipYard， 它有点类似一个 SOC template， 你可以把你的 code 塞到这个 ChipYard 里面，然后就变成完整的一个 SOC 这样。然后只是因为 ChipYard 稍微麻烦一点，如果你想要学respect sodo 的这个流程快一点的话，你可以选择有一个 branch 叫 sodo o 的这个 branch， 它是一个 standalone 的版本，就是比较好学，环境也比较好架这样。然后再介绍一下 respect from answer， 它是 respect 早期的一个 tool 之一，就是原本是一个 standalone 的 project， 后来被搬到 respect isr_sim 就是 Spike 的那个 repo 里面。然后它提供的功能就是最主要就是 host target interface， 就是让你的，比如说我现在这个 desktop 跟我的 simulator context 沟通，或者是 host 跟你的 DUT 沟通这样。提供就是简单的功能，例如说 elf file loader， 然后程式的启动或停止，或者是载入，然后或者是有一个叫 predefined 的 communication register， 就是to host 跟 from host。这个其实是一个后门，就是如果你要跑 respect test， 你需要把你的结果写到 to host 里面，让 这个 front-end server 知道说你的结果是成功还是失败。然后这是 respect 收到的 emulator 的 block diagram。然后因为 respect 收到它支援 respect 的 debug spec， 所以你可以发现它这边绿色有个框框是 debug module， 然后透过那个 respect spec 定义的 DNI 接到那个 debug transport module， 也就是 SYN-DTN 这边。然后这边外面会有一个用 system-level DPI 写的 SYN-DTN 点 cc 的一个function， 然后这个 function 就会去跟这个 DTN 对接，然后把 front-end server 给的资讯喂给 code， 然后就可以达到我们刚刚 front-end server 的功能这样。然后用 system-level DPI 好处就是因为它是 IEEE 标准嘛，所以就是其他 tool 也是支援的，但是就是你的C++ 那边可能还是要稍微改一下的。然后这个 flow 是它上面 license 上面写 Sci-Fi， 但是我不确定最原始的 flow 的那个 project 是哪一个，我猜是 Rocky Chip。就如果有人知道原始就最原始是哪个的话，可以告诉我。好，这是 respect debug spec， 你可以发现它就是把这一块 DTN 的部分取代掉，变成 SYN-DTN， 然后变成 DPI 去跟外面对接。有些 flow 是把外面这个 debug transport hardware， 就是例如说你的 JTAG 的 port 也取代掉，然后这样的话你就可以透过 remote band 的方式去跟 OpenOCD 还有 GDB 对接，这样你就可以从 GDB 去 debug 一个 code， 就很方便。用这个 flow 的人最有名的是 Rocky Chip。然后这刚刚的 simulation flow， 前半段就是因为 HTF 提供那个 argument pass 的功能，所以前半段就是透过那个 reset front-end server 这边去载入你的程式，然后之后这边会有个 loop， 就是 Veriter Clark Tick 的 loop， 它用来的功能就是检查你 code 有没有跑飞，再就是监控刚刚前面提到那个 to host 的 special reader 去检查你的 expect test 有没有跑对。然后蛮多 project 用这个 flow 的，就最有名的应该就是 Rocky Chip 嘛，就是 respect demo 的 project。然后它支援的就是两个，就是刚刚提到 DTN 的方法跟 JTAG 的方法，然后再就是 respect BON，respect BON 就是 respect BON， 就是 respect 一个蛮有名的 off-order 的实作。然后它目前不是 standalone project， 它一样也是需要去推这个 framework， 去推 framework 就直接把刚刚说的这个 flow 包好了。然后再来就是 ETHD， 就是苏黎世理工大学贡献给 Open Hardware Group 的 CEA6，另一个名字叫 Arian， 然后它也用这个 flow， 然后另外它有一个特点就是它还跟一个叫卓美九的 respect RV6 是 GC 的 emulator 做 code simulation， 这样。然后我主要讲的部分就大概到这边，然后其实有些进阶的 topic 各位可以自己去 study。就 Veriter 其实很像可以跟 UBM 跑，但我不确定它可以跑情况到怎么样，因为我不是做 DB 的。然后 Veriter 还可以吃 multi-class source， 就是像这个网站 EIPCP， 各位有兴趣可以去看，它是一家公司，应该是然后的 blog， 然后它有很多 Veriter 很精确的讲解跟介绍，还有一些神奇的招式。对，然后上面这个网站就是 Veriter 的官网，然后它其实不止 Veriter 这个 project， 还有像 Verilog Mode Pro， 反正就是一个好像是 eMake 的插件吧之类的。我记得有4个 project。然后我的报告就到这里。
好，在场没事，请问有，刚好提到几个，还是我提错换题，换题。对，收音的关系，请你到前面，那个麦是会录起来。
你好，那我原来在这里也是做地狱，所以我想问，你刚刚最后提到那个 Veriter with UBM 那个，现在目前是已经有在做了吗？还是说目前还没有人做这些东西这样，然后可能如果有的话到什么程度这样子？好奇。
其实我不知道到什么程度，但是我知道那个 project 已经起来，就是你在 Veriter 那个 organization 的那个其他的 project 下有 Veriter UBM 的那个 project， 然后很像国外有一家公司在 Veriter 的官网上讲了蛮多 就他对这个 tool UVM 的介绍还有实作，但是因为我真的不是那个专家，所以我不太懂他在讲什么。好，
麻烦，对，不好意思，我们这个场地比较。
刚好就是我们有知道一些就是关于 UVM 这边的，这样听得到吗？
听到。
对，那它其实就是像刚才提到，就国外有一家公司是 Ant Micro， 那他们在致力于做 UVM 这一块。那其实接下来的话，就是你们如果眼睛尖一点的话，其实Relator 有新的 branch 叫 V5 下一代的。那下一代的话，其实在这个近期好像会推出。那他们其实就是往这个 UVM 去做努力的，所以你们可以观察一下。补充一下。
刚才不介绍你的公司，我知道你是
我们有在做这个就是Relator 的 service， 对，那其实有兴趣的话可以跟我们做讨论。那其实我们也会跟Wilson 开会啦，所以刚才主讲者有讲到一个就是Relator Public， 这里也会出蛮多问题。对，那这个的话其实 Wilson 有跟我们讨论过用什么方法做比较好，所以如果就是在座有兴趣的，可以跟我们做一些交流。谢谢。
还有什么问题吗？
还有5分钟。
好。
那这边就是想问你一些问题。那对，那这个就是第一个，就是因为 Variator 这个东西刚刚很明显，它 test bench 是 C++ 写的，那就是我们常常会遇到就是 IC 那边来的工程师。对，然后他们其实对写 C++ test bench 有非常大的抗拒感。那我想你也在 Realtek 工作嘛，那应该如果要在公司里推广，也是会遇到类似的问题。那想看看你对这个有什么看法？那第二个问题是就是因为在IC House 里面其实不会只验一个 CPU， 它里面每个小 component 理论上都应该会有验证，对，因为 N2N 来只验 N2N 太弱了，对，那个Toggle 也不够多。那想请问如果想用 Variator 做这件事，你有什么建议呢？就是大概是这样的问题，就是 Submodule 的测试，那以及就是 IC 工程师对于用 C++ 写 test bench 的抗拒感。对，谢谢。
关于抗拒感部分嘛，因为我是资工系出身的，所以我没有抗拒感。对。然后另一个问题的话，所以我就只能回答到这里。然后另一个问题的话就是，如果你要做 unit test， 那就把 unit test 的 bug 切出来做验证，其实也是 OK 的。对。对。然后其实 unit test 好像蛮多其他的 project， 像有一个 project 叫 Coco TV， 一个用 Python 去一个 unit test， 但是我用Python，因为我不太会写Python。
我还剩3分钟，如果快问题1分钟内可以解决的话，但还有想问什么？好，要不然就在这感声带中，那就带完之后，那如果有需要的话，也是可以找他联络我。
应该会在最近或是 Prato 的那个摊位这样。
Hi. I will present you Nexus 5, which is recently developed out for the Superscalar software. So, a little bit of background first is that I'm mostly active on Spinacia, which is an hardware description library for Scala. Nexus 5, which is the software, and Nexus 5, which is subject of this talk. And my background is both software and hardware, so I will mix really a bit both worlds during this presentation. So, Nexus 5 it is a 32-bit and 64-bit with 5 core with a few extensions like multiply, atomic, single precision floating point, double precision floating point, compressed instruction set, supervisor, and user mode, which is more than enough to run Linux. Like for instance distribution like Railroad and so on, and it is also just enough to run Debian. So I'm currently working on that. Hopefully it will work in less than 1 month. So, and one of the main attributes of this core is that it is not implemented in the XLNOR system very well. And instead it uses software like it uses
a general purpose programming language, like let's say, it's like C or Python or Java. In the case of Nexus 5, it is Scala. So it uses Scala to elaborate the hardware and to build abstractions layer. And so you can find all the source code there if you want to. And here is, for instance, an example of the core running Dom in Linux in a reverse engineered oscilloscope at a quite decent frame rate of about 75 frames per second. This is quite good for the types of reason. So I didn't do type, somebody else did it. You can find some information here. And so I will not go too deep in the architecture, but I will give a few insights to get some feeling how this kind of core could work. So let's start by saying, okay, in the core there is two decoders, which means the core, when it fetches instructions, it can read up to 2 instructions per cycle to pass them further in the pipeline. 3 issue, which is how many instructions can start execution each cycle. And to do those 3 issues, there is 3 pipelines. One shared execution unit here, which does things like address generation unit for the load and store, multiply, divide, control status register to manage things like exception, interrupts, virtual memory, and these kind of things, and a few other specific instructions. And so this is a variable latency pipeline. And there is also 2 fixed latency pipelines, which have a better latency, faster wake up of depending instructions. And those 2 pipelines are equivalent, and they can do things like add, sub, shift, jump, and branch instructions. So in the core, there is a concept of physical register in opposition to architectural register. So by architectural register, I mean that, for instance, when you write some assembly code, you will make reference to some register like add x1 and x2 and put that in the register x3. So those are architectural register. And here in the core, I have more registers than this, so I have what we name physical register, which mostly allow the execution to go much further, to not having to wait in many cases that the previous instructions are done. Kind of allow to decouple the instruction stream in a few cases. There is a reorder buffer, which is mostly something used to store the context of the instructions in the pipeline. And so with 64 you could have up to 64 instructions in flight in the pipeline. There is some branch prediction. I will comment that in the next slide. Quite important to have a good branch prediction because this prediction penalty is quite high. It's about 10 cycles. If you compare that to another core, it's about double the penalty. Plus the fact that you lose all the things you already did in advance because you are out of other cores, so you may trash a lot of useful work. There is the notion of having a non-blocking the other cache, which means that if you access some memory which is not in the cache, okay, it will go to read that memory and fill the cache with it, but it will not block the whole system. It will allow the system to do other access to the memory meanwhile. And so, yeah, I will just talk a bit about the branch prediction because it is a kind of an interesting topic. Not saying that it is anything groundbreaking in Nexus 5. I would say it's pretty standard. But it is an interesting thing still. So the branch prediction is done in multiple layers. The first layer is done in the fetch stage. So it's very early in the pipeline. And so the thing here is that we don't have a lot of information to predict where the CPU should go next. We don't know the instruction we are executing yet, because we are currently accessing the instruction cache in parallel. And we don't know the data. For instance, if you have a branch if equals, we don't have access to we don't know the values that we have to compare to know if we have to branch or not. So we have to make prediction for those two things. And in the case of NACS, we predict which kind of instruction is in the word we fetch with the BTB. So for instance, if you tell us, okay, because we still have a few information here, we know which address we are fetching, and we know as well the history of the last branches, like we know the history of the last 10 branches if they branched or not. And so with those two information, we can predict a few things, like, okay, maybe it is likely that the instruction at that given one is branch if equals. And we also have to predict where this branch if equals would branch if we take it. So, okay, first part of the prediction. And second part of the prediction is done by the share, which is saying, okay, that branch in that word is very likely or not to branch, for instance. So it's a data prediction. So that's the first layer, which we have a really fast response time. And then we have a second layer, which is then in the decode stage. And at that stage, we have a few more information. At that stage, we know exactly the instruction that we are executing. We don't know the data yet, but we know the instruction, which allows us, for instance, if the BTB here told us there is no branch in that word, here in the decode stage, second layer, we can correct that eventually, if there is really a branch and told us before there is none. So we can correct a few things. We can also do some better data prediction in the case of call, function call and function return. For instance, return address stack is a stack structure in the hardware. When we do a call, we put something on it, and when we do a return from function, we pop something out of it. So that's the kind of improvement we can do here, and using that to do some prediction. And then, finally, for instance, in our execution unit, the job here is not to execute the branch, but it's more like to check. Because at that moment we have everything we need. We have the instruction, we have the data. So at that moment the job is to control, to check that the previous prediction did the job correctly, and if not the case, correct them. And finally then, when we commit the branch, commit means like we can apply the side effect of the branch. At that moment, we can learn. So there is kind of a loop allowing the branch prediction to learn from their mistake, for instance. And so, coming back to a more general view, abstraction doesn't mean overhead. In the case of this CPU, it got quite some decent performance. Keep in mind, it is mostly made to be a software, and so it tried to fit well in a FPGA. And for instance, in our RTX 7, it gets quite close to in-order software frequency. Still quite more resource usage, but it's not too much for that big design. So now let's dive a little bit into how you can generate the CPU, how the generation of the CPU is made. So, okay, you can go in the terminal, run this command line, then it will invoke the NAC65 elaboration, which is based on Scala as a shell-out-of-board programming language for the hardware elaboration. Spaniel HDL, which is, as I said, Scala hardware description library, and so this allows us to generate some VHDL and Verilog that you can then run some simulation and synthesis with flow you are used to. And on the top of Scala and Spanish, there are quite a few abstractions that I will now focus on the next slide. And so, Scala, it is an example of programming language, and here is an example of how to write a hello world with it. So, yeah, okay, nothing fancy. And okay, if you want to generate some Verilog file out of it, you could use the file API of the language. Like, okay, opening a file, writing stuff in it, string by string. But that's really not what we want to do, because this is how we want to do. And here is an example of the Spanish API, where you can, for instance, import the call, Spanish call, write a Scala main in which you invoke Spanish to generate some Verilog of a given module. And then, okay, let's say define A and B as input inside 8 bits and result as an output with the value A plus B. And this will generate this Verilog netlist. And so, okay, let's try let's look at this example, which is showing a bit the interaction between Scala and Spanish here. Because it seems a bit weird to write this like that while not directly writing the Verilog format. And so, yeah, here I will show a bit the synergy between Scala and Spanish here. So, okay, let's define A, B, C as output side 8 bits. Okay, let's then define array as an array buffer of units. So, array buffer is a Scala thing. It's a mutable collection in Scala. And so you can store a reference to hardware signals of the netlist like this, like, okay, we add A, B, C in our array. Then write, for instance, a for loop which will iterate over all the elements of our array. And we will assign each of them to 0. And how you can see here, the generated netlist will be kind of unruled. Because Spanish will only see the part of its API. Basically, Spanish is not a compiler. Spanish is the concept of having an internal domain-specific language, and it will register all the code to its API you do. For instance, you will see, okay, here he wants a new module, okay, he will add it into the netlist. You will see here, okay, he wants the output inside, he will add them. And he will not see this array buffer because it is a Scala thing. He will not see the for loop, it's also a pure Scala thing, but he will see the side effect of those things. Like, okay, here, it's assigning elements with 0. And it will generate this. So that's really the concept. You could use things like hash map, dictionaries, all sorts of data structures that you want to elaborate the hardware. And so, coming back to Nexus slide, if you look at the design, there is a lot of pipeline, a bit everywhere. For instance, there is one pipeline to fetch, one pipeline to decode and meaning and dispatch instructions, one pipeline for each execution unit, and quite a few pipelines in the load and store unit, like one for the load, one to manage the address of the store, one to manage the data of the store. Once those two things completed, there is another pipeline to apply some side effect, and another pipeline to finally write back the data. I mean, yeah, there is a lot of pipeline, which is maybe okay to write by hand if you don't have to optimize a lot, if you are really pretty sure of where you need to do what. But yeah, that's I would say kind of never the case. You always need to optimize things to move where in the pipeline you do some operations. And also quite often here, those pipelines are composed with multiple things running in parallel. So you need to compose the pipeline with different things. And so what was done is a pipelining API implemented on the top of Scala and Spanish API, where, for instance, here we define a module with A and B as input inside, result as an output inside. Then we use our API to create a new pipeline and a few states like A, B, and C. So the states will be collected in the same order they are defined and with this connection type. This M2 has been connecting with a register. So there is also other connections like instead of a register, use a queue or maybe directly connect wires from stage to stage as you want. And then, okay, we come here and we say in stage A, insert the value A plus B. And this will provide us sum, but sum is not a signal. Sum is a key allowing to retrieve this result along the whole pipeline. So we can go in stage C and ask the hardware value of representing the sum key. And assign that to the result. And then, once we specify everything we need, we say, okay, pipeline, build this up. And there you go. The thing is how it works internally, because here we have this build function. So how this kind of function is defined is, okay, pipeline is a class, and in this class we have a list of stages. So elaboration time list, and we have a build function. And what will be done in this build function is, like, for instance, we iterate over every stages, figure out what they need, where the things they need is generated, and generate the hardware required to connect all those things together. And for instance, what is a stage? Okay, it is a class, and here we have a hash map, like a dictionary, which will allow the stage to link a given key, like the sum key we had before, to its hardware representation in that stage. So yeah, we are using an hash map to elaborate the hardware we need. And so back a bit to Nexus 5 now. Just a few, for instance, if you want to instantiate the CPU, you have a single parameter, which is a list of plugins. And this list of plugins, okay, it's a Scala buffer, so elaboration time list of plugin. And in this plugins, we add like a plugin to manage the program counter, one to fetch instructions, one to decode, one to dispatch, commits, and quite a few others. And so those plugins, they are not on-off switches. So one concept in Nexus 5 was to avoid having a big bloated top level where everything has to connect with everything it needs, and as soon you need to add something, you need to go in the spaghetti mess to add a few modules, a few connections, and it's really horrible. So the concept in Nexus 5 is really, instead to use this list of plugins, if you look at the top level of Nexus 5 here, it's mostly empty, it's just a few lines and do not generate any hardware by itself. But instead, each of those plugins contain and define the hardware which need to be added to the Nexus. And it also defines some negotiation with all the plugins to ask resources. I will comment that later in the next slide. So, which makes things really flexible. Like, if you want to add an execution unit, like ELU0, you come and you add execution unit base, which is a skeleton of pipeline execution unit, and then you can compose this skeleton with a few other plugins, which will negotiate things with the execution unit base to implement their behavior, like add some instructions, adding shift instructions, branch instructions, and so on. And like, if you want to add a second execution unit to go faster with CPU, you just come and add another set of plugins with another key, like ELU1. And yeah, things will compose themselves. And so, okay, let's try to look a bit what is a plugin. So it is a class. Okay, in the case of branch plugin, we will use the branch plugin for the next slide. We need to know on which execution unit we need to work on. So construction parameter. And this class extends plugin base class, so we have the concept of inheritance here, applied to hardware elaboration, which allows us to define an early and a late phase. Because early phase will be used to set up things like we may ask to another plugin to provide us some interface, and the logic phase will be there to allow our plugin to generate some hardware. So, for instance, in the case of the branch plugin, we need to do two things. We need to detect if there was a mispredicted branch and correct it, and we also need to do an exception, a trap, in the CPU if the branch is misaligned. And so to do that, we need a schedule interface to put the CPU back on track. And the way we can get this interface, so yeah, it's not to wire things in the top level by hand, but it's more much more dynamic than this. So we will use some API from the plugin base class, which is like get the service which implements this software interface, commit service. So commit service is an abstract class, so a software interface. And we can retrieve in the list of all the plugins which one implements that software interface. Yeah, so like Kev has the base class service, the base class service, each plugin is a service, and there is a commit service, which is another service, and we have the commit plugin, which is a plugin, and implement commit service interface. So we really have a class hierarchy for our hardware elaboration. And once we obtain a reference to this commit service, we can ask him via the new schedule port function to provide us a new hardware interface for our own usage to put the CPU back on track. And we ask the interface to be capable to jump and cry. So yeah, that's the negotiation phase, for instance. And then in the logic phase, then we generate proper hardware to drive this interface with the dynamic condition detector, and yeah, we will generate the netlist required to drive it. So instruction requirements. So there was also the idea in the CPU that you could add its instructions easily in the pipeline without modifying 10 files there and there and there. And so, for instance, in the case of the branch plugin, we need to specify that we will implement a branch if equal instruction. So the way we do that is we specify what is a branch equal instruction. So okay, it is a single heading, whatever it is, and with a given opcode. So here is the bit mask representing the instruction branch equal. And a list of resources, like saying, okay, branch equals is using the integer register file, register source 1 and 2. It needs to read the program counter, and it needs to read the side of the branch instruction in byte. So yeah, here we define instruction branch equal. And then what you can do is you can retrieve the execution unit base, which has the same execution unit IDs and us. So yeah, this is a bit the same pattern than before, but here we use a lambda function, like really a software thing to filter out, because there may be multiple execution unit base in this plugin. And there is a function that you can call to add, to specify to the execution unit that a given instruction is implemented in its pipeline by someone, us in this case. And so this will have quite a few cascading effects. Like one side effect you have is the execution unit will figure out that somebody needs to read, needs the value of the integer register file as 1 as 2 and needs the program counter. And so the execution unit base will then add the hardware required to read those informations if it was not already made. to make them available for the branch value. So, and a few other side effects is like the execution base will then notify the issue queue and the dispatcher that it can execute a branch if equals. So yeah, the branch if equals can need to find its way through the pipeline, through the implementation unit. That's how it is sorted out. As well as the decoder, you'll be notified that when it sees that bit pattern, it needs to read those two registers. So the dependency tracker will know about it, and not really the register renaming system too. So there was also the concept of having composable pipeline. And here is an instance. For instance, the branch plugin we need to calculate where the branch has to go. And so, okay, to do that, we will retrieve the execution unit base with the same ID as us, like in the slide. And then, it will ask to the execution unit to provide the stage from the pipeline API, which represents the execute stage 0. Like you could implement your branch plugin over multiple stages, and here you ask the pipeline API representation of a given stage. And then you can use, for instance, the program counter key to access the value of the program counter key which was inserted by the execution unit base above the pipeline and drive the schedule interface. And so, yeah, another thing is there was a few issues with memory information that in and out of the core and superscalar core, you kind of often need memories with multiple read and write ports. So one way to define the memory in SpanielDL is that you can define RAM as being a memory filled with 256 words of 16-bit event. Then you can create a few write ports and a few read ports. But then the issue is that, I mean, it will work in simulation. It will work well in simulation, it will generate proper Verilog. But the issue is that many synthesis tools to put the design on real hardware will not be capable to handle it. They may be capable to handle when you have multiple read ports, but multiple write ports, it is tricky. So the way how things are handled in Axis 5 is the user can still implement memories like this in their pure way. And then there is some phase which will walk all the statements defined so far. And it will retrieve. Because basically, in Spanish, when you define things like this, you will feed a netlist representation, internal representation of the netlist that you can still visit. Like when you do some compiler techniques things, you have the concept of visitor, the concept of abstract syntax tree, AC, and here we are iterating over this tree, like saying, okay, in the current module, work all the declarations done. If you find one, for each one of the memory type, then execute this block of code. So here we have pattern matching. And you will get this in the terminal, because it will find this memory. And then what you can do is you can iterate over all the memory ports of given memory. Like to count how many write ports there is, how many read ports there is. And if you know that it will make issues, then you can modify the netlist. Like, okay, say memory.remove statement. That will remove the memory from the netlist, and you can replace it with something else. Like with maybe a black box, or maybe you will want to emulate memory of with this layout using multiple simple dual-ported memories with some live value table, or maybe using some XOR technique of the data to generate multiple write box. I mean, there is many solutions. And so, about simulations, in general, when we have to simulate things, we have to go to one of the big three simulators. But in an open source ecosystem, it's not possible for many reasons. Licenses are really expensive. There may be a few ways you can get something working without paid license, but it's really, really slow and limited. So instead, Nexus 5 uses Ventilator. So here is the full flow, where you can generate the hardware as we've seen before, Nexus 5, generate it from SpiceHDL, make it some Verilog. And the concept of Ventilator is it is a tool. You give Ventilator your synthesizable Verilog, and it will generate a C++ model, which is cycle accurate. It will only be able to translate synthesizable code, so it works well in our use case. So from that C++ model, C++ test bench that we have to implement, and Spike, I will come back on Spike in the next slide, we will compile all those guys together with GCC, and we will get an executable which will be our simulator. And for instance, here, our simulator, we can execute it with few arguments like to load a given benchmark, like the Rystone benchmark, a given memory, and it will execute in terminal. At decent speeds, it depends on the configuration of the CPU, but you will get between 100,000 Hertz, 100 kilowatts and 200 kilowatts of cycles per real-time signal. And so, to speak a bit about Spike, so Spike, it is, I would say, the official RISC-V simulation tool. So you can provide Spike a given binary and ask it to execute one instruction after each other. And basically, it will be used in our test bench as a golden model of what the Nexus 5 should do. So, and basically, it is used in a way to check that our CPU is staying in check with RISC-V specification. So in our benchmark, when our CPU Nexus 5 commits something, we will make Spike commit something and compare the result. So it's just a few, but it's not like letting Max run and log in something, letting Spike run and log in something, and comparing the two full execution log. It's really a lockstep way, because, for instance, when you have an interrupt proposed to NAX coming from outside, you have an interrupt coming from the outside, NAX will not necessarily take that interrupt in a deterministic manner. It really depends what it has to do. It may continue a little bit and then take the interrupt. And so for that reason, for instance, when Nexus 5 takes an interrupt, that interrupt is then proposed to Spike. So there is a few synchronization between the two models which are done like this to keep them at the same execution, in the same execution flow. So you can generate some traces, like in general, people are using VCD trace in the open source world, but with Ventilator, more and more we can use FSD trace, which are really compressed, and we'll keep track of all the signals of the CPU. So you really have the full view of the design with it, and you can also extract some interesting metrics, like, for instance, how much the ECQ is full, how much the IQ is full, stock Q is full, to see when there is some misprediction, when the CPU is executed into a new place. And you can also generate some GAM5 traces that you can visualize with Conata quite a manner. So this trace here is showing the execution flow, which instructions are executed when they are fetched in blue, when they are decoded and renamed, when they are waiting in the issue queue for dependencies, and in line it is when they are being executed. And here you can see the out of order execution in the core. Like for instance, this instruction, even if it's defined after this one, is executed before, because dependencies were already available. So it's quite interesting to look in that kind of graph to debug performances, to understand how the core work. And yeah, that's it. So here is a few links to with the doc, the GitHub repository, and the roadmap is getting Debian tested, memory currency and multi-core support, and eventually why not trying to target ASIC? Because currently it's mostly for software, but yeah, it could be interesting too. Also, thanks for Net for the funding, and now I should be here for the question.
Hi. Charles, can you hear me? Charles, hello. Okay, we're having some issue here. Okay. Sorry. Hello, can you hear me?
Yeah, I can hear you.
Yeah, sorry. I was unexpecting that I need to initiate a call. Anyways, so for the audience, this is Charles, who is the creator of the Next RISC-V and the Bash RISC-V, which is the very widely adopted software, and it won the actual RISC-V software champion back in 2018. So we're here open for questions that anyone would like to know about his newly created out-of-order RISC-V core. Yeah, we have a live one here.
Yeah, thank you for your presentation. It's interesting because from I know another language like Chisel, and it's familiar to your language Spiral HDL. And could you please have a comparison from your perspective for those two tools?
Any comparison with what? Sorry?
With Chisel.
With Chisel?
Yeah.
Mostly I would say there is a lot of history behind it, especially when Chisel was in the version 2, is the second version of Chisel. Now it's Chisel 3, so things change a bit, but I would say that now mostly it is about strictness and linting. SpiderGL is a bit more like VHDL, not letting you assign signal of different trees together. There is this kind of things, I would say. As well, the real way the names are handled is quite different. So overall, I would say a lot of little details. And one big details is that SpiderGL integrates a library with all a large library, a much larger library than Chisel in the base language, like UART, SPI, a lot of peripherals and buses are included in the core. That way, different people working with SpiderGL can use the same base.
Thanks a lot. So basically, Chisel is more like just a power digital language, and on the other hand, the Spino HDL is equipped with many toolboxes and a lot of simulation framework there. So this is kind of the system Verilog to the Verilog comparison. Do I say correctly, or or do I misunderstand something?
I will not go to that extent because basically Fusion and Spinal share the same paradigm. Just to be really clear, just because the interpretation and the details are really different, that provide a really different experience. For instance, Spinal here keep the whole abstract syntax tree of the netlist. He keeps the whole netlist in memory, while Chidel flush it really fast into the FER RTL format to go further with the flow. And he has, for instance, quite a few side effects like Spinal here can track much more precisely issues because he keeps for each potential signal, he can keep the whole stack trace of the context in which the given signal was created. So it's really a collection of implementation details which can make quite a big difference at the end.
I see. Thanks a lot for your explanation. Nicholas would like you to send follow-up questions, or?
Okay. I'm also very interested about your Spinal HDL, and could you explain how did you do the Verilog integration?
The question about Verilog, what is it?
Okay, in GISO, we use the FIR-RTL to elaborate the Verilog. In other words, to generate the Verilog code. Could you explain how did you do it?
So basically, Nicholas has.
It goes.
Yeah. You go ahead, please.
Yeah. Oh, so yes, question is how it goes to Verilog, right?
Yeah. Yes.
So it goes. Just to do the full path. So when you use a Penguin API, if you fill an netlist in memories, there will be a few transformation phase, a few check phase, and then it will go directly to Verilog or to the HDL. It goes directly to it. There is no intermediate file formats.
So basically, the Spinal HDL is directly being translated into the synthesizable Verilog without the FIR-RTL-like intermediate.
Right.
It's directly translated from the high-level language to the synthesizable Verilog. That's the paradigm using here.
Okay.
Yeah.
I got it. Thank you.
Thank you. Do we have any live question here? Okay. Still, I have some questions I'd like to ask. Charles, I'm wondering that if I want to fund you, giving the funding to do another extension, could you give me a rough amount of the budget? Because you know the VexResPy is very popular, and now you have the NextResPy, and people are thinking that maybe they can donate money to you to implement some more complicated extensions, such as the PackCindy or even the vector one. So I'm wondering, do you have any amount of budget you would like to receive to implement this kind of advanced extensions?
So vector one will be something quite complicated. I would hope to not think about it too much because it is really a big one. But Pack SCMD, it's really hard to know how to tell. I guess, my main issue is time.
Okay.
That's my main issue. Like, I really have a hard time finding time, so I'm trying to focus on not too big extension.
I see. So
like a few custom restrictions for specific usage, yeah, that's feasible. If it's really something too big, it really depends the moment and depending what I have on the hand. And then if the project is for open source, I would say I'm mostly flexible on the amount. As soon as it is reasonable, I will not charge consulting fees for something open source normally.
I see. Thanks a lot for your impressive answering. And do we have any questions here? If not, then yeah, we have a live one.
Hello, I just curious about your low VR speculate logic strategy. Do you fully support low store of order or just only low low cache hit prediction?
Sorry, which kind of out of order are you asking for?
Do you fully support of order of memory instruction or only just support low cache hit latency prediction?
I have issue understanding, so I will just try to repeat to be sure I'm right. So you're asking about the memory system, right, for the low store?
Low store instruction.
Yeah. Sorry?
Yeah, the question is right. You're repeating it right.
Okay. So where the load and store out of memory works currently is that load can be done fully out of order.
Okay.
Store will not block loads in any ways, and there is a store to load bypass which is implemented. So the data cache is able to refill multiple lines at the same time. So the cache is non-blocking. So overall, I would say the memory system is not bad in that regard. Does that answer fully the question?
Okay, thanks.
Yes, I think that
there is also. Yeah, go ahead.
Yeah, maybe that I will forward your. Could I give him the email address from you that, or the public one you published on the GitHub link? Maybe he will try to.
Yeah, sure.
Yeah, okay. I will send over the contact info for him for the more deepen asking. Yeah, and thank you a lot. We are having a session prior. I know it's very early for you, so good morning and goodbye.
Right, thank you. Bye.
再说不好意思，那个就是我因为法语腔，其实我听得不是很懂，对，我觉得对。
好，
那你忙。Hi, Matt. So allow me to introduce a little bit the person here. This is Dr. Omin Lee, who is the there's a kind of echo. So he is the lead. I would say the lead of the Taiwanese semiconductor education. So I'm inviting him to join us, and he will do some kind of live Q&A after the session. So yeah. And please go ahead to share your screen, and we will, without further ado, let's do your talk. Thank you.
Yeah, sorry I joined a bit late.
That's perfectly. Please go ahead, and if it's okay with you, please go ahead.
Okay. So thanks very much for inviting me to do this presentation. Very happy to be here. There's a rich history in semiconductors around the world, but especially in your area. And now, of course, there's the huge impact of all the fabrication that's going on there. And I've only been involved in ASICs for the last couple of years, so I'm very new to this. And I'll just introduce a little bit about myself right now. I work for Yotis HQ, who you may know do open source synthesis tools, and those tools are used in all the open source ASIC flows. And we also do formal verification tools, also open source. I have a course called the Zero to ASIC course that aims to teach you everything you need to know to get your own chips made.
Sorry for
and I'm also involved in a...
Sorry for interrupting. Dr. Poe, Dr. Lee, could you mute a little bit? There's a lot of echo from your end.
Oh, okay, sorry.
Sorry, Matt, please go ahead.
That's okay. I was wondering what that noise was. And Chipflow, which is a startup that is aiming to make the most of this new oncoming open source semiconductor tools to help get more product companies making their own chips. So if you're interested to find out about any more of those, you can check the links in the presentation. And I'll be sharing a link to this presentation later on. So if there's anything, I've got lots of links in the presentation, and if you want to do further research, then you can use the presentation as a jumping off point. So just before I continue, Ruanland, is the audio and the video, everything okay?
We cannot see your slides. Did you just disable it, or will you reshare it again?
No, they should be shared.
Oh, sorry, so your slides is gone. Can you reshare it, or sorry?
Is that no? That's good. Is that working?
Yeah, it's here now. I will ping it to the.
Okay.
Could you change? Okay, I will do it from my end. I will change the layout so it will be on the. Okay.
Great.
So please go ahead.
Yeah. And if it stops sharing again, let me know, because I aim to be sharing the screen for the whole presentation. I don't mean to turn it off.
Okay. Please go ahead.
Good. Okay. So let's take a quick review. So thanks for the amount of time that you've given me today. There's quite a lot of time. So I'm going to give a quick review of what has happened over the last 2 years in this space, because things are changing very quickly. And I'm also going to give you a demo of the tools in action and show you the kinds of things that we're getting out of the tools. So let's start off with the quick review. So in 2020, we had the open source Sky 130 PDK, which is, as far as I know, is the world's first open source process design kit. And that's important for quite a few reasons. One, makes it much easier for people to get involved without having to sign an NDA. So if you're doing educational work, that's a real key thing. And the other thing that was announced was having a free opportunity to make your own chips. So I had actually just started playing around with some ASIC tools, a tool flow called QFlow. And I was getting GDS, which is the file you need to send to the foundry. But when I found out how much it was going to cost to make the chips, I thought this is probably not going to be something that I do much of. But when Google decided to pay for the free shuttles, so there's a lottery system, there's a shuttle that runs about once every quarter, and there's 40 slots on that shuttle. And if your design is open source, you can make an application. And I've applied to all 6 of the shuttle opportunities, and my designs have been accepted on 5 out of those 6. And I've had about 10 or 12 different chips made now. My first use of the open source open lane tools, I'll talk about a bit more about the tool flow later, made in July. I did a presentation in November, and I did my first tape out with a group of other people in December for MPW1. That was the first free shuttle opportunity. In 2021, eFabless, which is the company that provides engineering experience and helps us interface with the foundries and has done a lot of the work on getting the open source PDK and the open source tools working together, brought up one of their test chips, so that was good to see that things were looking like they were going as expected. and in May they announced a commercial version of the free shuttle. So that's $10,000 for 300 chips. Then in June we had the MPW2 tape-out date. In October we got MPW1 silicon back, but due to some problems in the tool chain, which I'll mention a bit more later on, we thought that it was going to be a complete write-off due to hold violations. So if you're into silicon, you'll know what that means and how scary that is, but if you don't, then I'll explain a bit more later. November, December we had MPW3 and 4 tape-out. November we also had RemoteCon 2021. I finally got my own chips back from MPW1 in January, so it was a whole year for that process. Ideally, things are going to go down to 6 months or so, but this first one took a long time because it was the first run through of the first PDK and then new tools. MPW5 was March, MPW2 wafers came out in April, and MPW6 was in June, and we're expecting MPW7 in September, and there's more foundries coming online and more PDKs coming online later this year. So that brings us up to the present date. So I'm just going to give you a bit of information now about my own first chip. So because when I first started with 8, I've done a bit of FPGA experience, but I wasn't really used to how much space we had available. So on these shuttles, it's 130 nanometers, which is large. It's quite an old node, about 20 years old now. But 130 nanometers is still very, very small. And we have 10 square millimeters in this space here that we're allowed to use. And so I was finding that my designs were very small. So I did a collaboration with some other people, and we put 9 designs here. 8 designs that have a kind of a function, and then this big block at the bottom is a big multiplexer that can set each of the designs to be the one that is controlling all the IOs. I've got lots more information about MPW1 if you want to find out more on this link here. And like I said before, I'll be sharing the link to this presentation at the end of this talk. So we had these 8 projects here by me and some friends and mucks. On the chip at the bottom part, this part here, we have a RISC-V processor and 2 kilobytes of SRAM. And we have a bit of firmware here that can decide which design should be enabled. So the MUX did work, as we found out that MPW, my chips works, but there was quite a few problems I had, largely because I was doing everything by hand, because it was the first time through, and we didn't have much time, and I was very worried about making some mistake that was going to render the whole chip useless. So I was very happy when the chips got back and I got all my designs working. It wasn't that straightforward because I mentioned that we had these hold violations, which I'll mention a little bit later on in the presentation. If you want to get more information about my MPW designs, you can check this out. So I thought what technical talk would be complete without a demo. So what better way to show this stuff than doing a demonstration. So I've got the tools installed on my computer here. Just turn on the environment. I have tools for lots of the different shuttles here, so I'm activating the tools for the 7th shuttle with this command. And we have this PDK here, which is 2 gigabytes installed, and it's now very, very quick to set up the PDK and the open lane ASIC tools. It takes about 2 minutes. I'll give you more information about how to set that up later. And then we have this open lane directory, and inside there we have a design directory, and then in here we have a list of all the designs that kind of come as examples. And and I'm going to be using this one called 7 segment seconds, which is an extremely simple design. This divides a 16 megahertz clock down into seconds. Then it uses a bit of sequential logic to count, and then a decoder with some asynchronous logic to decode that into a 7-segment display. If you're used to Verilog, which is the hardware description language I use, this is extremely simple and straightforward, but for people who aren't familiar with Verilog, I'll just give a very quick run through. Verilog is a way of describing hardware, so it looks like C, but it's not really C, and that can be quite confusing when you start off. We have this definition of the ins and outs of the module, telling it that I want some registers, which are kind of roughly comparable to variables, although these registers will be created as actual real hardware chains of flip-flops in the design, rather than being register spaces in a CPU, like if you're using a programming language. And then I have a sequential circuit here, which is triggered only on the clock, and it basically does the comparing, counting up to 16 million, and when it rolls back over to 0, it adds 1 to a digit. So this is going to be creating 2 hardware adders and some comparison circuitry, and then take that number and put it out through this 7-segment decoder, which is asynchronous logic, which means that as soon as an input changes, the output, so it's like a big collection of ands and ors and nots. And essentially, as this decimal number comes in, it puts on the 7-bit output, the 1s and 0s necessary to turn that number into a 7-segment display. And I can synthesize this and show you how Yosis will take that hardware description language and then turn it into a digital netlist, and this is essentially what gets sent into the OpenLane tools. So, going back to OpenLane, this is one of the available tool flows that we have. It's currently probably the most popular one. It's the one that I know most about. We put our design in the beginning. We use Yosis to do the synthesis. We do static timing analysis, which can measure how fast the circuit can run by looking at the digital logic that is used to create that circuit. And we have a feedback loop here that we can do some iterations on to get better timing if we need to. The current design for test is currently not implemented. We come back through here. Everything in this green section here is provided by OpenRoad, which is a set of applications that has been under development for 10 years or so, is funded by DARPA in the States, and is aiming to create a full open source ASIC flow. And they provide these floor planning, placement, optimization, and routing stages. Then we do antenna diode insertions, which I won't talk much about, but is important in semiconductors to get good yield. Within the semiconductor industry, there is a huge amount of depth. The supply chains are enormously long. The software is very complicated. The physics of how it all works is very complicated. So this whole talk and presentation is at a very high level, assuming not much knowledge. And so I could talk or experts could talk for hours and hours about any one of these points, and I'm just giving a very brief high-level overview of this whole flow. Then we do detailed routing, come back through here. We extract the whole circuit, including the resistances and the capacitances of all the wires. And then we do another static timing analysis to see if where the cells have ended up and all the routing, how these wires are connected together, whether that's going to change the timing and mean that the design is going to work or work too slowly. And then we stream out the GDS2 files, which are the files, if you've done circuit board design before, they're a bit like the Gerber files that you use to send to the factory. The only difference here is we've got about 40 or 50 layers that we send instead of the normal kind of 4, 8 or 10 layers that we send to a PCB fab. You can get the tools downloaded from here, and I've also written a summary tool that I'm going to be using in this demo here, which knows where all the locations of the intermediary files are. So let's run OpenLane now on these tools, on this design. I'll come back up to OpenLane. It's provided as a Docker with all the tools installed, so just mount the Docker there. And then I'm going to start running the tool. Seconds. Let me just time it as well. This is a very, very small, short design, so it's pretty quick. It'll probably still take 3 or 4 minutes though. And as that's running, I'll start a new terminal. Just using my summary tool now. And we can look at some basic stats as the design is working. So this is the list of the standard cells that Yotis has decided we need. So to build 7 segment seconds, we need 430 standard cells broken up like this. So we've got AND, OR gates, AND gates, buffers, inverters, muxes, 3 types of NANDs, some NORs, ORs, plenty of different cells here. There we go, this one is flip-flops, so we needed 52 flip-flops for that, because we're going to need at least 24 for the seconds divider, and then another 12, 16 for the digit counter. Let's just take a quick look also at, in the PDK, we get all these standard cells that we can use, and I just loaded them all up. So all these different cells that I just mentioned, here we have on the left-hand side, we've got about 140 of them. So if we take that DX flip-flop, you can see this is the standard cell. These are the layers that are being used to make it work. There's about 24 different transistors here, all connected together, and it builds up that flip-flop. And if we now take a look at a much simpler standard cell, this is just an inverter. If the input goes in high, the output comes in low, and this is built with complementary MOSFETs, CMOS, so we've got N-type MOSFETs at the bottom and P-type MOSFETs at the top, and they're joined together into push-pull arrangements. We've just finished this, so that whole flow took 1 minute and 44 seconds. Let's continue with our route through. So we've just looked at synthesis. I'm going to go down now to floor planning. So floor planning is looking at, working out how much space we need, working out where the IOs are going to be, and giving us a kind of area. So let's measure this space. So this is 140 microns square. And then let's look at the global routing. So now this is given us the power distribution network. So these plus and minus lines run through the design. And then all these standard cells have now been placed roughly kind of close to where they need to be to fit to the pins, and also what functionality they're going to be fulfilling. But one thing is they're not snapped to the grid or aligned very well to the PDM yet. So that gets done in detailed routing. And now everything is on the grid. Things should all be, see all these big cells, those are the flip-flops, they're all kind of grouped together because they're forming these registers. We've got the IOs. And then the final stage is generating the GDS. Then now we have all the routing between all the cells, all the missing spaces being taken up by filler cells. And here we've got a list of all the different cells in use, and I can turn those on and off. So for example, I can turn off all the decoupling capacitors that are used to fill up the space. Now we can see, what's this one? Down at the bottom, decap 12. It's funny, it's normally in alphabetical order, and I've already turned off the decap, so I'm not sure where that one is. But you can see there's more space now available. So the efficiency, the density of this design could be even smaller, but we just wanted to get the tools done quickly. So this is now the final design for that 7 seconds. We could now integrate this into a design to EFAB, send it off and get our chips made. So when you want to make a submission to eFabless, you do get this whole 10 square millimeters. This part here is always present, which has a RISC-V core and some memory and some stuff to help you do the bring up, which can be more complicated than you want sometimes. And then we can put our designs in here. Like I said, we had problems with this 7-segment display countdown with all the designs we put on MPW1 because we had hold problems. And those are caused by not having enough time for the flip-flops to register data correctly. And unfortunately, you can't fix those problems by slowing down the clock. But we were able to get things working by very carefully undervolting the whole design and slowing things down. And that whole thing was caused by a misconfiguration in the tools so that the clock tree was synthesized in a not very balanced way. And that has been fixed for MPW2 and forward. So if you want to find out more about that, you can find out about that on this link. But I was very happy that with a little bit of work on getting the voltage right, this tiny small design here, I did actually manage to get it working, although I had to kind of fake it because I could only get 6 out of the 7 segments working at once. But that video is a demo of my design, of that design that you just saw being synthesized with those open source tools, being put onto the eFabless shuttle, being made by Skywater Foundry in the US, being packaged, being sent to me, mounted on a test board, and then running that design and actually getting the output. So that was really, really fantastic step for me. My first very simple designs working on an ASIC. But now is a good moment just to, am I still showing my screen? Yeah. Now is a good moment just to mention that one of the ways that I'm now involved in this space is I run a course called the 0 to ASIC course. So 200 people have taken the course and we've submitted designs on all the shuttles. It assumes no prior knowledge, so this is a really good way of getting involved if this does seem interesting to you and something that you want to find out more about, check out the course. I've also been working with eFabless to help with the messaging and creating documentation, and I recently did a half-an-hour video that did a complete run-through from downloading and setting up the tools, putting a simple design on, to running all the tests, to generating the GDS, to sending it out to eFabless and getting the chip submitted to the shuttle. So that is about a half-an-hour watch on YouTube, and you can check that out. You don't have to pay or anything. I'll just have a quick drink of water. So for MPW2 and onwards, I moved to a more automated design handling for putting people's designs together. So with the course, we typically take, not always up to 16, but around 16 or so designs, and we put them all together onto one submission so that we can make the most of the precious silicon. And each project has all the inputs always connected, but the outputs go through a tri-state buffer. So if they're not turned on, the outputs are floating and they don't affect the bus. But a bit of firmware can turn on the tri-state for a specific project And you see that's what these highlighted lines are here. If I want to turn on this project, I turn on this line, it activates the tri-state buffers, and then the outputs of project 0 control the outputs of the actual chip. And I've successfully used that from MPW 2, 3, 4, 5, and 6, although we're still waiting for silicon to come back. It's now out of the factory. MPW 2 is being tested right now, so I should be able to validate that this all does work. So fingers crossed for that. So now let's take a quick overview of the tools in the space. That was something that Ruan said that he was especially interested in, so I wanted to include that in the presentation. I built a list of a whole load of open source ASIC resources on a GitHub page, so you can click this link and get a big page of loads of resources. And these ones at the top are kind of the more digital focused tools. So you have OpenLane I demoed, OpenRoad is less of a complete flow, but you can still use it. It takes a bit more work to get running. Silicon Compiler is another end-to-end ASIC flow, as is Coriolis 2. OSS CAD Suite contains all the FPGA and synthesis tools that you would need for doing FPGA development. And we also have OS FPGA and VHDL support, to just mention a few there. On the analog side, we've got Magic and K-Layout. K-Layout was a tool that I was just using to show the GDS, but you can also use it to draw. XScan is a way of doing schematic capture, and also builds into synthesis, simulation. Mosaic is a more modern schematic capture. ngSpice is a simulation tool for analog, and Zeiss is a kind of an upgraded ngSpice, more modern, being funded fairly heavily, can do parallel simulation, which is important because the analog simulation is incredibly slow compared to the digital stuff. And GDS Factory lets you draw GDS shapes very accurately and is in use for photonics. So what's missing? That's an important question. We do have everything we need to do digital and analog designs all the way through, and we're getting results back. But we do have tools that are missing for RF designs, which is important. We want to be able to do things like radios. We're lacking full wave solvers. We've got only a few different types of analysis. We don't have harmonic balance, transient noise, etc. They do exist, but we haven't kind of checked them. We need to actually start doing verification. We could do with improvements to the physical verification. We need this to be scalable for new PDKs. It takes a lot of work at the moment to add a new PDK to be able to be used in this process. Better mixed signal simulation, so if you're doing an analog and a digital design together, you want to be able to check that everything works together as you expected, and that's actually a lot harder than it should be right now. Design for Tester said that was one of the things that was missing in the OpenLane tool flow. Design for Test here, you would want to insert a scan chain or a way of being able to easily access the interior parts of your project. There's work in progress there, but it's still under test. Simulating power, simulating clock and clock distribution, and also a library of proven analog IP would be great, like a big block of analog to digital converters, clock drivers, SerDes, gigabit Ethernet, all this kind of stuff. We're waiting for this library to get built out and be tested and be useful so we can use different bits and pieces and know that it's going to work together. So having said that, let's take a look at some of the example projects that have been taped out over the last 2 years on the open source flow on the Google Free Shuttle. So MPW1, there was a very interesting processor taped out that aims to run MicroPython and had a bunch of USB peripherals, and one of them, especially the USB peripheral, is microcoded, so it's a very nice bit of IP. So the idea is you could take this USB block, drop it in, and then with a bit of microcode, set it to be an audio interface or a keyboard interface or a mouse interface, whatever you want. This little nice screenshot here is a PLL for a 3 gigahertz radio. Thomas Parry is building amateur satellite radio transceiver, and that's a very interesting project. Fuse RISC is 2 RISC-V processors with some custom FPGA fabric in between them, and the FPGA fabric is supported by YOSYS and XPNR. Subservient is a tape-out of SURF, which is a very, very tiny RISC-V processor, the smallest one. Analog neural networks. MPW3 saw some testing of some other tools, so Coriolis 2 and FlexCell, rather than using OpenLane and the standard PDK. An 8-bit A to D, and RISC-V Arduino. MPW4 saw some space-hardened stuff, a fun transistor in the shape of a skull and crossbones, radiation-hardened chip. MPW5 saw a Delta Sigma audio DAC, micro-ops, which is a new type of processor coming out of from Anton Blanchard from IBM. OpenFASOC is analog generators, programmatic analog generators. MPW6 saw a 10-bit SAR A to D, some ReRAM tests, and some chaos generators. But these are just very, very brief sample projects. If you want to have a browse through, then you can use the eFabless website, and I've also just written a command line tool that lets you list all the tools and search them by their tape-out status, or use grep or whatever you want to search for the descriptions of the projects. I've just heard a ping on the message. Let me check what that was. A message from you? 20 minutes left, notification, thank you. So just a word on RISC-V. I did a presentation for RISC-V Japan recently, and I did a bit of data mining, and over the 6 shuttles there's been 270 RISC-V CPUs taped out. I did a little bit of a breakdown here. We've got these other CPU types here, but RISC-V is the dominator, and then split up by type. These are all the different types. There's a lot of active development and testing going on with RISC-V in this space. And now I'm going to talk a little bit about some of the related work in the field. So, SRAM characterization. We have an SRAM generator block that generates the IP that we use for the kilobyte SRAM if you need to use fast memory on your designs. But we didn't really know how well it worked, so Andrew Zinenberg did some very interesting characterization with a test board and an FPGA. And as we get new versions, we can mount it on this test board, plug it into the top of this board, and then run through this test again. If you want to find out more about that, you can check this. He really knows what he's doing in terms of high-speed signal integrity and analysis, so it's a very interesting set of videos to check out. We had a fully open source ASIC focused conference last year that I organised, with a lot of interesting talks spread out over 2 days. There's WOSET, Workshop on Open Source EDA Technology, where people send us papers and we review them, and then there's a 2-day schedule of presentations, and you can check out the papers and video presentations that were given in 2021 here, and it's also being organised for 2022. There's been a lot of work now in putting the ASIC tools running in the cloud, especially as either Jupyter notebooks or GitHub Actions. So Propi has been doing a lot of interesting work in enabling CMOS simulation and running the OpenLane tools and browsing the GDS files, and that is really great for doing academic work and being able to share your results, or educational work and avoiding big downloads. So if you imagine being able to let your students do simulation of these standard cells that I was talking about earlier, like ANDs and ORs, but being able to do that all within the browser without having to download gigabytes of tools on your classroom computers, there's a huge amount of potential here for education. something that I'm especially excited in. And we've got GitHub Actions. I've been working on a few GitHub Actions that can do things like installing the PDK, installing the tools, running the flow, running all the tests. And these are the kinds of things that I use for people on my course to make sure that the designs are all working. I recently had a very interesting interview with a guy called Teo, who's been working on bringing up the open source synthesis tools up to parity with proprietary tools on matching the performance of their hardware adders. So previously, Yosis would always synthesize the same type of adder, which is kind of in the middle of this performance space. But if you wanted faster or smaller adders, for example, you couldn't choose those. So he did some very interesting work with allowing different types of structures of the carry chains of adders that allow you to specify, I want an extremely fast adder because it's for the ALU of a RISC-V processor, or I want a very slow but space-efficient adder because I'm just doing like this 7 segment seconds example that I showed you earlier, and I just want my design to be really small. So more information on that here if you want to find out. And we are testing his designs on MPW6. So now I'm going to spend a little bit of time talking about tiny tape out, which is something I've also been discussing with Ruinland. And it seems like we're going through a bit of a Sputnik moment at the moment. Everyone wants to make sure that they can have the skills needed for working in the semiconductor industry. We have these huge, very spread out, long supply chains. People are worried. We've got the EU and the US CHIPS Acts, and more people are talking about education and getting more people into the pipeline to be able to be working on semiconductors in the future. Obviously not just a question of the material being available and the opportunities being available, but also that people think of it as a valid career choice, and we see that working in software is currently something that people are preferring due to better salaries. That's also something that needs to get fixed. But the educational side of things is important, and Tiny Tape Out aims to bring the barrier to entry lower for design and manufacture of ASICs to high school students, or makers, or entry-level courses at university, open source silicon enthusiasts, but ultimately creating the opportunity for all high school tech students to design and receive their own chips. So it's a big goal, quite a difficult one to meet, but this is an idea of what we could do to enable that. So I've already got a lot of experience with my own course, and something that's very important is that the course should be standalone. So you come into the course, you have an introduction on how the PDKs work, you do simulation of standard cells in a web browser. There's no downloaded tools for this. You do some problem solving with digital logic, you build some combinational logic to start with, and then you move on to sequential logic and build these very small, simple circuits. And each segment of the course should be supported by templates and solutions, video introductions, and additional resources if you want to go further. You build your digital designs in the browser, so I've been working with Uri Shaked, who's built this cool website called Walkway, which is mainly for Arduino simulation, but he's adapted it for us to use with digital logic, and we have this very simple standard cell library here. And I can give you an example of a running simulation in the browser. I can just press the play button here. I've got a 10 kilohertz clock signal coming in, and then these 12 clock dividers to get a slower flashing LED at the back. And we're running this simulation at 100% at real time. And Walkway now has an API which allows me to take this number and use that to get a Verilog netlist, which will be useful for the next section. So let's move on. These are examples of the kinds of things that you can build in a very small area. So these are all 470 by 70 microns. So these are some of the first kind of tutorial lessons, 8-bit counters, like this one is like the 7-segment display, so you can see it easily fits in that 70 by 70. I think we've missed a slide. Here we go. So after we've got the URL, that number from Walkway, we can use a GitHub action which builds the GDS in the cloud. So I can come here, edit this make file, change the number here, and then when the GitHub action runs, it will automatically install, download the tools, and generate me the GDS. So again, I don't need to install anything or download anything, and then I can see the result of my design here. So this is the layout, and I've also got all the information here on the reports, the final summary report, the synthesis report. So we're going to give everyone 100 by 100, everyone's going to get 8 ins and outs. You can run through this whole process, and then at that point, you'll have experienced the process and you'll have learned something about digital design and ASICs and semiconductors. But now there's a paywall, so now you can optionally pay for your design to be manufactured, or your school pay for you. We're aiming for $100 would get you your design on a chip, mounted on a PCB in your hand, and $25 would just get your design on a chip. So why would you bother with just getting your design on a chip? Well, that means you can then, as a school or a hackerspace, you can get an even cheaper price, because you could get a workshop of 10 people, 9 of them just put designs on, 1 of them gets the design and the chip. Because all the designs are put on the chip, that means that the chip you get back can then be used to test all 10 designs. So that brings the cost of participation lower, and you get your hands on the chip that has your design on it for a very low price. So how do we put all these designs on? My current working demonstration, which I'll be taking out on MPW7, features 500 designs at 100 by 100 and a little driver in the corner that can use the scan chain. So because it's a scan chain, things are slower, but for beginner digital projects, that's no problem. We can still run them at 100 kilohertz. And we get 300 chips back, and those would then get mounted onto a PCB that we can then send out to people. So if you want to find out more information about how the scan chain works, you can check this. During this process while you're waiting, so that's one problem, 6 months wait is a long time for young people to wait. We're looking at ways of accelerating that. But you would get emails about basics, ideas for designs, this week's coolest voted design, virtual factory tours, information when the wafers are out, information about when the PCBs are set up and sent. So that's tiny tape out, and I've got another few minutes, I hope.
Yeah, around 10 minutes. So
10 minutes left. Yeah.
I will ask around if there anyone here want to ask questions.
Yeah, if you can get a list of any questions, and just in the last couple minutes, I'm going to do a very quick summary of what's happening next.
Okay, so no one here, no one live here is going to ask questions. But Dr. Lee, could you bring some comments or questions here?
Yes, yeah. Next.
Let me just finish. Let me just finish this off. I just need 2 more minutes.
Okay.
So we've got multiple educational projects happening. We've got the IEEE Chipathon. We've got lots of funding happening in the space. We've seen the EU and the US Chips Act. The EU Chips Act specifically mentions open source multiple times in their investment plan. We have a huge amount of community growth. We've got the 90 nanometer PDK that's just been announced last week from Skywater, and we're expecting another 130 and 180 coming soon. And now's the time to get involved. So download the tools, follow my video, take my course. Next tape out is MPW7 on the 12th. As a thank you to being invited for this presentation, I've made 5 $200 discount codes for my course. You just need to use CostCup22 as the promotional code. lots of resources here, and feel free to connect with me on LinkedIn or Twitter, sign up to my newsletter, and if you want to check out in detail any more of what I've been talking about, then the slides are all on this link here. So that's it, that's my presentation. Thanks very much for your interest and your time. And yeah, if there's any questions, then I believe we've got 5 minutes left.
Yeah. Dr. Lee, just go ahead.
Okay, thank you, Matthew. Your slide provide a very interesting and a very promising process of open source EDA tools. And since the time is limited, so I would like to ask you, can you share with us your experience to avoid the failure you encountered in MPW1, so that we might be able to bypass this fault processes, so we can learn how to create a right way to create a ASIC from ourselves. Thank you.
Yes, good question. So the OpenLane tool is meant to be an end-to-end flow that you put your design in and you just get the design out. That's like the aim, but things don't always work like that, as we saw for MPW1. But really the best way that you can help with that is just to get involved and start making designs, because the more designs we have, the more tests we can do. And when the problems with MPW1 were found, they were fixed in the toolchain. So you can use the latest tools that don't have those bugs. That's the easiest fix. But you can also read the source of the tools, and you can make your own fixes and make your own pull requests to the open source tools. And that's one of the great things about the open source tools, is that there's a very quick iteration time in getting these bugs fixed quickly.
Okay, thank you.
You're welcome.
So we're having actually around 3 minutes left. So I would like to ask something that Matthew, how is the TinyTable adaptive? How is the adoption rate? How many? You must be lobbying around the high schools. How many high schools have been already adopted the TinyTable program?
Well, TinyTable is still in a very in the idea phase. So at the moment, I'm explaining the idea to people and presenting it, and trying to find collaborators. So I want to work less with schools and more with people above the schools who can say these 10 schools would all be interested. So I'm also working with academics in university bodies, and there does seem to be a lot of interest, but I'm still kind of waiting for the person that can say, I am working with making sure that schools are teaching relevant technology. This looks like a great thing, and we want to run it across these 30 schools to trial. Then that will be the moment that I will kick the design off. Either that, or for MPW7 for the tests, I'll just make it free to participate, and we'll see how many people we can get involved just to test it out.
Okay, thank you a lot. So I will, because we are having another speaker already here, so I will be ending this part. But Dr. Lee, I know you must have a lot of questions you would like to ask with Matthew, so I will hang up from my side, but you can continue to discuss with Matthew if you want, if you like to. So here we go. Okay, I will go to another session.
Yeah, thanks so much.
Yeah.
Thank you. Yeah.
Dinesh, could you hear me?
Yes, I can hear you.
Yeah. Oh, sorry. Just give me 1 second to adjust my. Oops. It's kind of messy here because I just switched from one side to another. Okay, here we go. You're up and online, and let me. Without further ado, let's introduce Dinesh from India, who is working on the pin-to-pin compatible RISC-V SoC, which is very, very interesting. And just go ahead.
Okay, thanks, Arun. Let me share my. You are able to see my desktop?
Yeah, yes, it's very clearly. Yeah, please go ahead. Please go ahead.
Okay. First of all, thanks for the invitation. Share my experience on the open source shuttle and one of the project what I am sharing. So about myself, I have around 20 plus year experience on the VLSI design. I have worked a lot on the most of the aspect of RTL to GDS flow, from architecture to taper, and also I have a lot of experience on the post-silicon development system like that. In my career, I worked on most of the commercial tapers around 180 nanometer to all the way down to 10 nanometer. So I worked in a companies like Cypress Semiconductor, Centillion, and currently I am working in Intel as a design manager at Intel India. So let me start my presentation. I just thought I just give a brief background on what is this Open FPW Shuttle project what we are discussing. So this is sponsored by Shuttle, which is sponsored by Google, and it is managed by an EFWS team, and the tapers are done in the Skywater foundry, which is a 130 nanometer. And if you see the main points are, there are 40 free shuttles are given per shuttles. These slots are available. And currently the way it is running, I see there are 4 shuttles are there per year. This is an approximation I am just saying. The main requirement is to keep the design complete in the open source. Your design you need to keep it in the open source. And the cost of the fabrication, packaging, and the file evaluation board and shipping it to everything is covered by Google. And in this, who have got the chance, they are going to get a 50 parts, packaged parts, and 5 development board, they get it. So if you see how the actual design is going to sit within the open shuttle, the EFWS team has created one harness where they created their own small RISC core here. If the projects are without any RISC core, you need an external way to configure it. You can use their RISC, small RISC is there, which you can use to configure it. And for a user angle, they given a 10 mm square free space. So whatever design we develop is going to fit within that, and your final integrated chip will be looking like this. So it's a 38 pin package, and the pins are already frozen, but you have control whether they is given a some way you can manage this IOs and you can control it. So this is how what the MPW shuttle project. So about my experience, actually I started on open source shuttle around December 2020 times. I think that time exact the MPW1, which was already announced on the 2020 December, which I was not attempted any of the project on that one. So but I started for the MPW2, which was around the June 2021 timeline the paper was planned. So since because of my sort of experience, I don't want to do a small project. I thought of taking a basic RISC-free based SoC design. So I thought maybe that's what I should do as my first trial. So but when I started, it was like it was a tough ride for me. Actually, I thought it will be a smooth ride with my experience, I thought. But when I started using the tools, I see a lot of issues. Most of the issues you can see the system error, limited system error support was there in the simulator and overlap and synthesis. So whatever SoC design I picked, nearly I need to modify nearly 20 to 30% of the design to match compile the simulation design and say able to simulate within the simulator and synthesis. So that took my lot of my effort, and I done to and fro to find out is it my design correctly working and simulator working. And some of the places tool was compiling but synthesizing, but it is totally optimizing the design because of some specific system relations syntaxes. So I can say it was a tough way to simulate it, construct the simulate is not totally optimizing the design. And also, since only there are limited complex SOC was there, only NPW1 was turned out, I have very limited references to cross-check flavors. And also in the flavors, I found it was like a totally a lot of instantly was there. In NPW2 time, I see each macro to synthesize it, it was two was taking one or the other place. It made synthesis clock free. And power routing, global routing, one of the other places who are working. I need to close a bug report on the corresponding tools and those iterations. So it was, I can say, it's a lot of effort that gone in my first step in experience there. And also, one of the things what I saw was how the tool, the porting, the mechanism they managed. And so the concept what they done is, first there was the independent, the open source community tools are managed independent, the YOCs, Iverlog, Magic tools are independently managed by the independent open source community. Those are picked by open team and they are merging it and creating a open lane tools. So one of the main issue was there was open lane team, open road team was picking a version which is somewhat older, like a 3 to 4 months, 6 months older on the main branch. And they are collecting it and creating open lane. And that open lane, once again, each is taking it and creating their own additional patch and releasing it to the open source, our open source shuttle project teams. So whenever there was a bug and when I report into the main source tools, when they fixed it, taking that to throw the flow itself was becoming a big problem because of the additional patches what each of those team used to add. So it was like, because of that, I was posed multiple issues to find out how the tools work. Mechanism is there to break it so that I am able to complete my taping activity. So overall, these all things took me more than 6 months to understand how the flows are implemented. But finally, after around 6 to 8 months, I got cleared my tape-out checklist. And one of the things I observed is during MPW is there was no clear timing closure mechanism. So they were more on the GDS clean database than the timing closure. That's what the stress was there. And even though I raised multiple times, there was no less follow-up was happened around the timing closure. So this is what was my first experience in the MPW2. Next MPW3 was around 15th November 2021 time. That time since I had some experience in the previous one, I tried 2 tapeouts that time. And this time what I see it is somewhat better managed in the sense that the open road team himself was managing the total tools directly giving. So the additional patches what each of this used to do, that got removed. So effectively whatever the open community tools were directly can be easily ported. So that reduced a lot of efforts on my side. So whenever I see a new bugs are fixed in the main tool, porting became somewhat easy. So with that, and also because of my previous whatever the effort, it helped me to clean up the tapeout activities well within the timeline. And I can say it's a bit smooth ride for me at least compared to MPW2. And MPW4 to MPW6, I done around 8 tapeouts. So and I can say it's a bit smooth ride because of the total understanding what I built upon the previous tapeouts helped me. So around next 3 MPW, I nearly taped out around 8 shuttles. We'll go through brief on some of these tapeouts, what I have done. This is just to flash what are the tapeouts I done in MPW shuttles. So around 8 recipe-based tapeouts I done and around 3 non-recipe-based tapeouts I done. And you see in MPW2 time I attempted only 1. In MPW2 3 times I attempted 2 MPW shuttles. In MPW4 I tried 2. And in MPW3 5 I attempted 3 tapeouts. and MPW6 I attempted the 3 tapers. We'll go a little bit on each and then the project, what is there and what I'm drawing there. So this is the first project what I draw in the MPW shuttle, MPW2 time. And here we basically what I took is I took in Santako RISC 32-bit core, and I built an Shippo interconnect and added he called SPA master to talk to the external flash, because there was no inbuilt flash was there, the flash memories were not there in the Spy Foundry, whatever libraries they share, we don't have any flash memories. And also I integrated an SQL controller for data the data memory purpose, for the RISC to have a data purpose. And also I added some peripherals like a UART, I2C master, and USB 1.1 host. This was my first MPW2 papers, and in this, in the design wise, I made a lot of changes in the system level logics around this to match to simulator to work within the open schedule tools. And one of the things I can highlight is that with this whole thing, the tool set was I'm able to only meet the timing with 50 megahertz only. So I made each blocks, these main blocks, these whole blocks comes in a different clock domain against this core. This core had its own clock domain, but till finally the current tool, MPW2 set was able to only meet the design of within 50 megahertz only. This was my first attempt at what I tried in the MPW2 time. So this is one of the non-RISC based papers what I tried in the OpenShuttle, which is like which I tried for MDIS controller, where in MPW2 time there were some SRAMs are developed by the other teams, and I took those SRAMs and I built an MDIS controller where it is going to test how reliably these memories are coming, and I wanted to validate my MDIS also, which is required for my future development. So I added the MDIS controllers. So here basically I put 4, 8 memories. Some are 2 KBs, some are 1 KB. So basically I tried an MDIS controller with 8 MDIS controller and 8 memories. And this aim is just to see my MDIS controller and also how this SRAMs works. And here one important things I taken care is I given a 4 location memory required options I given in this MDIS controller. So that is a picture I wanted to validate in this MDIS controller. So next one is just a upgrade version of the previous MDIS controller where I tried a logic bit. So the current OpenShuttle doesn't currently support the scan method, where there is no way you can implement a scan and validate your design implemented correctly. So I done some hacking in the flow, and I built an 8 channel scanning scanners. I took the previous MDIS test this project and added a serial scanning and created my own LDIS controller where it creates the peer-based pattern and runs for a duration and checks that the final signature matches with the border. This is just to check how the scan is going to run in that system. So this is the project which is one of the non-RISC project which I turned in the OpenShuttle. So now let's come back to the RISD now, which is the one which I'm mainly driving, at least I tried, nearly I'm trying the 8 tables around this architecture. So this is an 32-bit RISC based SoC design where I'm trying to target where pins are matching with the Arduino platforms. So if you see it, this was a somewhat upgraded version of my first RISC core. And I made some little bit changes in design. I added a cache, instruction cache and data cache, and a tight memory added. And I split the core into 3 splits. The main control of the RISC core I separated out, and I built an interconnect so that if I want to add a multiple cores I can connect it, and so they connected directly through the commonly supported an iCache and Dcache order, and there is a common architecture created for the wishbone interconnect where individual peripherals can be connected. So I connected the quad SPA master and two UARTs, I2C master and USB 1.1 host and SSPA. And the ADC, actually I am not integrated, I am looking for community help to integrate this. I am more expert in the digital side, unlike I need some help. So industry monitoring with something in the open source things I can fill and add it here. So currently ADC is the one which is missing in this design. And apart from that, I added a pin mux. The aim of the pin mux is to match the pins as it in the Arduino. So the things wise. So one more thing I added is I given booting options. So there are 3 ways you can boot the whole chip. You can go through the Caravel has its own wishbone interface. You can go through that. You can boot the whole chip. You can configure it and wake up the RISC port so that you can even through this. You can configure the external flash, and once you program it, then you can wake up the RISC port so the system brings up that things. So there is one more mode I given is a UART. So UART mode also there is a message handler I built it here. The external, if you are connecting through the UART, you can go and configure. As it comes as a master, you can go and even configure the flash. I given a standard write and read command for the serial port. You can go and configure it. Even though Caravel interface was not working, I can go through this and then I can boot the whole system. That was the given a backup options here. And third option I given is the SPA slave. So this is something similar to what you see in ISP in Arduino. I made a same pin compatible to ISP where you can through the SPA of the ISP you can go and configure all the flashes and you can bring up the chip. So there are 3 booting options what I implemented in the it is not like in the first version I supported in MPW, because I can say over individual MPW I done some improvement. These are the final design work focus here. And one more thing is after MPW 6 onward, I am able to meet a timing at least at 100 megahertz. So previously, as I told in the first one, the maximum time I am able to close is only 50 megahertz. But with the tool improvements and some design changes in the pipeline, now currently the design is able to meet at 100 megahertz, which is I can say is a good improvement from the Rosheta. And one more thing I can say is actually the design wise it is not like a one single clock domain design. So I implemented multi-clock domain designs where RISC core has its own clock. It was a core so that the timing of RISC core is not deciding the rest of the clock domains. So system clock has separate clock and this is built with separate clock. So implement on the RISC core can not the timing of the RISC core is not influencing the system core timings. So basically created a hierarchical based design so that it simplifies in backend things. Nearly most of these blocks are independent hard macro inside the design. These are the main highlights of the project, and here just to show it how I am trying to map the Arduino with the Atmega and Arduino pins. And here the pins which are listed in this white color are the Arduino pins, what I am trying to match with the Atmega pins. These rest of the pins are what Atmega and Arduino is having it, and I am trying to match these pins. And wherever the Ds are there, they are digital pins, and unlock A for unlocks. And apart from this, actually, whatever the Caravel projects given 38 pins, and what I needed was only 24 bits. 24 bits. Rest of the pins, since there is no internal flash and SRAMs, I use them SRAM and flash purpose. Until we have an internal flash option, currently I am totally dependent on the external flash to boot the design. But rest of the 24 pins I try to match with the Arduino flash. So if you see, currently I am driving 3 projects on the Arduino, and so I try to create some generic concept so that when you add more cores, it will work transparent. You see, currently the first one, Arduino S4 is a single core Arduino, where I connected only one recipe core, and really rest of the cores are main functions are same. And the second one which I am driving is multi-core type is a second recipe core I brought in here, where rest of the interfaces other things are matched, but the interconnects have some changes to support the second core here. And one more I am supporting is the quad core. So currently I am supporting the max up to 4 cores. So that is basically because of the whatever free space I have in the open range shuttle, which is 10 mm square. Currently I am maximum able to fit that 4 cores. That's what these are the 3 currently I am driving, and most of the time I am attempting 3 tapeouts, one with S cores, a D core, and a quad. Just to set how the physical view is going to look, because normally we have a doubt when you do an SOC with the 10 mm square, how much space you would have switched, whether there is any empty space to add new function, and those questions comes up. So that's the reason I added this my placement view of each core, just to have an idea how this design, how much design is congested, or how much space is there, and if you want to add an additional IPs. So you can there is a spaces there or not, just to highlight an IP on this view. You see the S core, around 30% of the design is free. So it is around the total instances, 94K instances are there, and 85, in that 81K is the combo logics and 13K is the sequential flops are there. So it is around 100K instance design. In that I can see around 30% design is free. That means if I have some additional IP, where I can go and add it. So it is not so congested, and I am looking as the tools are getting improved, so the utilization of the input it should have it, and you should get a smaller area it will take for each IP, so you will get some more IPs you can plug it. So I can see the 10 mm square is a good space to play around to create any board and IoT. And just to see a little bit dense deep core with still the 15 to 20% free space is there. This is around 120K instance design. The quad core is somewhat congested, I can say. This only less than 5,000 free space is there, which I reserved for an ADC here. Otherwise, it's nearly filled space. And that's the reason I stopped at a quad core, because there was no much space left for me to add additional cores. This I see around 160K instance design. This is just to give a brief how this Arduino over the period can help over the Arduino. Just I try to put my way. See, currently, if you see the Arduino, there are fixed memories are there, flash memories. If you want to take anything, you have to bring one or different configurations of the Arduino to build it. Since currently it is on the external flash, you can go and add an additional flash. It's up to 64 MB, there is no limit on whatever flash you want to add there. And so if you want to do an add-on, so you need typically in Arduino cases you need to bring the new boards, new chip configuration you need to bring. But here you can design, you can add those configurations into the Arduino project itself, so that you can create your customized chip, which nearly matches like in Arduino. Means you can even compare in Arduino environment itself. One thing I missed in my discussion time was, it is not only pin compatible, it is going to run in the Arduino IDE itself. So you can even run your C code in the Arduino platform with the package, the Aristino. You can compile it and you can use that in my Aristino project. So currently I can stick to 8 C code of the Aristino Arduino software I ported already. I am cleaning up one by one the firmware. Hopefully within some time I will have a very clean Arduino platform there. And you see some of the Arduino features missing, I can see the keyboard, some of those features are missing. You can go and add those into this SOC. And also if you want to reduce the design, so Arduino is okay, it's already hard and correct, but since this is a soft IP for you, these people can use that to reduce some of the IPs which you feel not required, and you can decide what IP is required and you can go and optimize it. And this is still valid for your power and performance also. You can go and squeeze that design so that you can get a much better control the design. This is just my first thought on the Arduino project when I started. This is just to show what happens we open source shuttle is what are my just going back and open source shuttle just to say what are my pinpoints and what are the issues currently I see in the open source shuttle. So one of the main issue I can see is even though papers are happening as per the date, chip delivery is not happening. So even though I done my first paper in June 2021, still I have not received my first chip. So it is already running 1 year back. Hopefully EWS will take it seriously and try to get some chips as early as possible so that our silicon iteration will complete. So that the next chip will be comes out in a better shape. Otherwise we are just whatever the issues we are thinking from the verification angle only we are modifying. We are not getting the silicon data, which is I think is one of the critical thing is missing. One more thing I can say is the MPW shuttles are continuously, the tool flows are continuously getting changed. The projects like AskMe, mine, which is uses the previous shuttle to continue, so once again I need to readjust this flow. So from my angle, if you see, I am looking more for the tool improvement than the flow. I feel flows are somewhat okay, I don't see much changes are required. I am looking for more in the tool improvement. But currently I see both are getting into a change. But readjusting them is also is becoming one type of pain I can see. Third important thing I can see still some critical functions are missing in the open source shuttle program. Like even the SRAM is there, only 1 KB and 2 KB, only 2 types of SRAMs are released for the people to use it. But also not fully qualified, so that is a risk we are carrying. And I don't see any flash or EEPROM currently available for user to use it. Another thing I can say is that LEC and the scan is still not, those functions are not integrated, so we have a big risk. If you want to thinking for a commercializing papers, this paper can use for commercial purpose, still I think this critical function missing. I see it's still we need to use this to say we can use these papers for commercial. And also low power methodology, I don't see the direction how we can go to even low power methodology to reduce the power, propagating those things. I don't see a clear methodology. And one more thing which I see is to directly use my chip into actual any commercial or any boards. We should I see the Caravelle default harness setup. Because if you see currently already Caravelle team have their own recipe code, and I also have one more recipe code. This is like a duplicate recipe code. So that handles to just to create a proof of concept where you want to create, then I need to keep 2 flash, which is somewhat deviating from the standard board configurations. I think that's one thing I can see is a critical issue one can see from this chart. As a summary wise, what I can say is it is a great opportunity for the university and researchers. For the software people, since all the tools are open, there are plenty of opportunity to it. So all the source codes are available in the GitHubs. People who are having a good idea, they can go and use it, improvise it. So it's a good opportunity for all the idiot software people who want to contribute to the open source. And also for the research community in the various domain also, we can plan their new chips around new ICs around IoT healthcare applications. These are the things that I have it for this today presentation. That's all.
Thanks a lot for your wonderful experience on sharing this, and I'm very, very surprised that you haven't received the MPW2 chips, because from my understanding that they should be already sent to their participants. So this is kind of...
MPW1 will be there given. MPW2 they are saying August end there.
I see, and I can completely agree with you that the users needs tool improvements instead of their fancy flow improvements, because we are the users of the open land, and we want to use it to do our projects just like yours, your risk domino, which is very inspiring, and we want it to work. And also the harness SoC from eFabless is kind of restricted to users. I can agree with you that because many people here in Taiwan are actually thinking that maybe we can use the harness, use the MPW sponsored MPW shuttle to do their test trips, and for tiny or the Soho. Sorry, the screen flickers, so I was thinking that I was disconnected. Anyway, so many Sohos and many makers are thinking that they will once think that they can use the free shuttle to do their products, but this is not the case, just as you say, because the harness chip is there, and the I/O control is very, not very working, because from my understanding, the people from, if I remember correctly, that some people are complaining that the GPIO control from the harness chip is actually broken. Yeah, so that is very sad. But regarding your slides, I have one thing we wish to ask. That is, you have mentioned that you have many RISC-V cores. You have the double core RISC-Uno, and the 3 cores unit RISC-Uno, and the 4 cores unit RISC-Uno. So how the cores interact with each other? Do you have any kind of mailbox that one core could notify another core that what it is doing, or is it just plainly use some kind of polling mechanism to communicate with each other?
Currently, this hardware semaphore waves are making. And because each correspond IDs, and it is echoing.
Can you hear me? Yeah, I can hear you.
You can't hear me?
Sorry.
Can you hear me?
I can hear you. Sorry. Did I say something wrong, or?
No, I am not able to hear you. I am able to hear you, but you are not able.
We're having some kind of connection error, so.
Can I hear you?
Okay, so hi. I can hear you. Can you hear me?
Yes, I can hear you.
Yeah. So actually, I just want to ask that do you have kind of a mailbox for your RISC-V cores to connect with each other on your RISC-Uno, or it's just plainly via the memory swapping kind of stuffs?
It is like mailbox only working.
Okay, I see. Thanks a lot for your wonderful project. And do we have any projects on the field? No? Okay, so thank you very much, and we wish you a great success in the following MPW shuttles. Bye-bye.
Okay, thank you.
们下一场会有一段时间之后，就是各位如果想要先离席，我隔壁其实有一场那个就是 Whisper Advisor 的，如果各位对那种比较有兴趣的，或许会觉得会比较适合，因为这边其实就是咖啡会比较，也就是加上讲者有口音啊，所以就是听起来就会比较辛苦一点。就是隔壁那边因为是葡萄牙人，不过他因为长期在就是这种 conference， 所以他的口音会相对来说比较是台湾人比较轻松可以听得懂的。所以有兴趣的话，可以可能等一下这场会是日本人啊，所以也是口音也是比较重一点的。如果各位是比较想要更 participate 更深一点，可能隔壁那一场讲 advisor 会，20啊，
那个是3点开始的。
我其实手上，因为我现在手上没有那张表。
有没有wanted to know about open source？
对，是的。Nicholas 果然是专业的。对。
今年 RISC-V 的主题怎么会这么多？
我觉得也跟因为它的 ISA 是 pattern free 有关啦，就是当然你可以说 MIPS 也是现在就反正也很便宜，可是就以学术界来讲，大家一定是喜欢这种 open pattern 的人啊，对。所以
我以为是什么，比如说 C 有赞助啊或什么之类的。
我们公司有赞助这场研讨会，就是我们是 Golden Sponsor。OK。那我们的确也是像接下来这个讲者，我快速稍微 take up。就是我们的确也是有像有一些 open source 的 code， 那就会希望说可以让就是讲者可以做不讲者，让我们的 partner 可以可能 maybe 先做前期的测试啊，跟 take out。对，像我们这场就是他拿我们的 open source 版本的131去做他的 production 的一些 prototype。那其实像对啊，我其实我这边其实就很好笑，我穿着我前公司是那个就因为那边有麦，我就不讲前公司是什么，然后现在在 Sci-Fi。对，那他们
所以正确的讲法念法是 Sci-Fi。
对，我们像我们 CTO 是那个 Young Subley 勇哥在念都是念 Sci-Fi， 然后那个 Christian 就是我们的CEO 跟 Co-founder 也是念 Sci-Fi。
OK， 好的。
对，然后我快速讲，他就是说我们的 policy 是尽量希望可以 enable 一些客户，那我们的买控有一些其实 license 都很便宜，然后甚至是 open source， 像这个客户就拿，他原本是用我们前公司的 code， 就是后来就看到你有就是 Sci-Fi 这边有 free and open source 的 code， 那想拿 evaluate 一下，就这样去做 prototype。对，所以其实是一个还蛮 free 的一种，就是 free to engage 啊。对，因为其实很多公司你这种要 evaluate code， 可能都要签 NDA 或什么，就
NDA 都要的。
对。那这边就是但也如果你要比较好的，那当然要签 NDA。可是如果你只是 want a taste of the RISC-V， 然后 some basics of peripherals such as the interrupt controllers or stuff like that, it's free and open source. You can just take it from GitHub. 我后面这一场其实很担心会不会黄掉，因为其实他最后才敲定，然后他当时又有，因为他其实有些 slides 是他的 partner 的 property， 然后他就来回 check 了很久才说他可以讲，可是后来他 email response 又不是非常的 responsive， 可是我就已经反正我是打算说，就是他如果真的不行啊，因为反正我后面那一场我是有很十足的把握，我后面那一场其实他讲者是做 APJ 开发版的，那他跟我很熟，所以我可以很自由的用他的时间。
后面那一场你说这一场的下面那一场？
对，就是日本往后面就是最后一场。
OK。
那是讲那个 open source 的 APJ board 的 design， 比较偏那种 PCB design， 就是我们这边也叫 FOSS-enabled hardware project， 毕竟再怎么讲也不是就是 Sci-Fi 成果发表会这样。对，所以我们一定是会要尽量各 diversity 的这种 topic 都要 include 进来，包含 PCB 的 design。就大概是会是这个状况。这场接下来应该是35分，对。对，你们先忙，我今天有可能会黄掉啊。其实我觉得你们如果真的有想听的 topic， 先去听他旁边的 topic。对，就这个我现在到现在那个日本人还没进来，我不知道什么状况，对吧？
那个刚才那个什么？RISC-V 在前面那个的 slide 是在哪里可以看得到？
我会找他。
他讲的还不错哎。
对，他讲的很好，对。
对啊。
说他从设计到 PC。
对啊，我原本之前看那个 OpenNet， 但是我还没下手。
到马克 application， 我有点害怕，我先处理一点事情，不好意思。OK。这可能先让我，对不起，我有那个 business card， 就是我 LinkedIn 也 OK， 就是对不起，我现在这边我现在真的有点手忙脚乱，我那个 business card 在这边，真的不好意思，我先处理一下那个，就对。
Raspberry Pi 4，这台 Raspberry Pi 4 Model B 也是通过 System Ready IR 认证。不止如此，其实 Raspberry Pi 4 Model B 也通过了 System Ready ES 的认证，就是说它支援 ACTI， 这个我们晚一点再谈。好，帮我下一张。好，那各位在买板的时候要注意一下 ，System Ready IR 目前是有分成。
没事，抱歉，我刚因为那个我现在两轨，所以我现在手上有点乱，对。
所以日本人出现了吗？
还没。对，可是反正我最后一场那个时间非常非常 free， 我跟最后就我这一轨最后一场，我跟他讲说我会需要非常 flexible 的搬动他的 session。OK， 然后
如果真的日本突然有问题的话，可能就提前。
没有，他只能延后了，没办法提前，对。好恐怖哦！一直听到 notification， 可是东西不知道在哪里，靠腰。我上面，到底哪里在喷那个 notification？
非常赶时间的。
啊什么？
就是35分那一场。
35分这场就是
日本还没出现。
日本还没出现，对。哇塞，真的没有啊，真的没出现，不知道什么状况。我是因为当初其实谈得很临时，所以我连他的谈的，就是我是连他的，就我只有他 email， 对我没有他任何其他的联系手段，然后我现在非常的凶，天啊！因为跟他是有改过一次时间啦，所以他如果他完全是，我先，
还好，这边人没玩多。
对，就如同刚刚有跟在场有些人讲，所以我比较想听，就是比较口音比较没什么问题的。隔壁有一场那个3点会开始的，真的要打岳阳电话吗？好像有他的代表号啦。有联络到他了，可是他说他会有sign in，可是我现在安安sign in什么状况？Hi, Kawasaki. So sorry for the I know that the arrangement has been kept changing, and I'm very sorry. My sincere apology to all the inconvenience.
Oh, that's no problem. So, are you guys ready?
Yes. Yeah, we have plenty of. Let me show you around. Here are our audiences, and they are very eager to know from your experience and also the RISC-V Tokyo days. They are very excited to know things about it.
Okay, thanks. So let's see how that goes. Let's see. All right. Yeah, this is it. So do I, have I shared the screen?
Yeah, it's up and running, very clear. And
Okay, great.
Okay, you can just start your session. And without further ado, let's give a big hand to the speaker.
Okay, thanks. My name is Shunpei Kawasaki. I show up as the second author because this is about the chip development. And I'm titling this presentation Marmot RISC-V SoC Leveraging Open Source ISA IP Process Development Kit and Immediate Tools. And then I collaborated on this effort with the University of Electrocommunications. So today's agenda is I'll have a short introduction about lightweight IoT that we did in 2016. And then now we are working on the bridge structural health monitoring IoT. And then we talk about some little things about the hardware security, like remote IoT authenticity proof, and open source software security, such as root of trust chip integration over the SOC update, and open source Marmot RISC-V SoC finally, and then future directions in summary. So SH Consulting has been around since 2013, and then we also have this subsidiary in Vietnam, 2014. And we have been, in our prior life, we did the SH Flash MCU chips, embedded software and hardware, and development tools, video games, Java card, secure MCU, firmware, and PIPS Part 140 certification. So we did, since like 2013, we started out a ultra lightweight IoT, and which actually only weighed 108 grams. And then no one else actually pursued this like lightweight IoT side. So when the volcano activity started in Kyushu Island, we had top share for a very short period of time for drone transported IoT. And in 2019, we decided to just actually increase further that application market size to capture this infrastructure IoT for structural health monitoring to be applied to bridge. And in the meanwhile, we did all sorts of things like designing consumer equipment, motor controller, and automotive ECU, but I think what happened was that IoT survived. So that in 2018, suddenly like the Sakurajima just erupted, and suddenly like they needed the drone to just actually host IoT to a very dangerous area where sulfuric acid gases around. And then in like that, we use that wireless IoT. And in the 2013, we have been always trying to just actually do that, like implement RISC-V. And we finally wanted to do it by having one of our guys just actually started as a PhD student and then used the academic fab. And then this is based upon ROM 0.18 micrometer. And then we use the same exact rocket SoC generator to generate this chip. And it is like that 5 meter by 5 meter, 180 nanometer long shell with a fairly reasonable amount of 64-bit architecture, RV64 GC. And in the meanwhile, that this whole mammoth IoT system has been developed, and this video shows an example. And essentially, what this does is like it doesn't have any cable connection. Everything is done by the wireless.
Mr.
Essentially, that's hi. Yes.
Mr. Soros, I'm so sorry to interrupt, but I'm not sure if you're showing your slides or because your slides freeze at the very first page.
Oh.
So I'm wondering if, so I was thinking that, oh, it's very long intro, but I was thinking, no, you're referring to some pictures. So I'm thinking that
right.
that shouldn't be the case. Yeah, sorry for interrupt. And
can you slide now?
Yeah, I can see the scrolling to your slide. We are now on slide 7. Now it's 8.
Okay, that's good. So I'll just actually use the slide like this, rather than using that
the
full screen.
I see. So okay. So I will share around your slides after the talk, and we'll keep going here. Okay. From here, it's okay. Okay, thank you.
Okay. So like back to the chip topic. This is the chip that we did in 2019 using academic shuttle. But the only problem with the academic shuttle is we can't carry this chip outside of the campus. Because, of course, like once you build a chip, you have to just integrate it into the board and then just actually see and software integrations and so forth. But so a restriction by the two companies didn't allow that to happen. So what happened was essentially we have a very good experience, but then we just actually started back to this board system, system development, which we call mammoth system. And so the way that it works is like that you just put on a different part of the bridge things like gateway and then endpoint. Then typically like that you use like multiple endpoints for like the gateway, and then every sensor that and an actuator that shows up in this type of setting is all connected to by wireless. And what it does is essentially, there's this displacement that the bridge causes, and then over the season, it displaces, and every day because of the temperature, displacement changes. And then you capture and then monitor, and then somehow you are able to figure out what kind of structural health that the bridge span has. Actually, this is like more like how the companies that are using those type of IoTs. So the type of application needs is like long-term, no maintenance, like 5 years of like usage, left as is. And of course, it has to be harnessed its own energy, solar energy and lithium batteries. But since it doesn't have any kind of cable whatsoever, the installation is very cheap because you only have to just nail down those devices and then program. And also, obviously, like you would like to have the over-the-air software upgrade from remote location. Also, obviously, because this is like regional government and they don't have a whole lot of money. First of all, there are 700,000 bridges in Japan, and about 9% of them are just owned by municipalities rather than the central government. And they don't have a whole lot of budget to just actually burn on that monitoring bridges and then decaying infrastructure. So this is more like very, I'm not sure about the marketing, but yet, like it moves slow enough that we can catch up as a small thing. But anyway, so using the consumer grade components for low cost is like one of the requirements. and also system security against hacking. If all those like a boxes are just hacked by someone else, it's going to be all sorts of sad, like incident. So therefore, that we didn't really want to have that happen. And another thing is, so this is like a set, very like looking very cheap using that off-the-shelf boxes. It has got the gateway master, slave endpoint, and sensor and actuator. And suddenly we move into this like RISC-V thing. So as we are using like RISC-V IP as a chip for this system, and then the type of like RISC-V that we're going to be using is at the bottom here, linked to the chip that has got Altos on it. Over the years that we have developed both like Linux IoT and an Altos IoT, and we found out that Linux IoT, in the end of the day, it consumes like minimum 5, and in some cases 50 watts of power. Compared to that, like Altos IoT can actually run some tasks on 50 milliwatt, 100 milliwatt. Because like the memory is 1,000 times bigger than Linux IoT compared to Altos. Anyway, so we did the demo in 2019 using like the Founders board on the RISC-V, integrating with the secure element. And then we started doing more and more of like the things like OTA integration into RISC-V. And then finally we came up with this notion that the free Altos RISC-V porting in 2021, that you do need relatively large flash memory and RAM in order to run this free Altos secure connection to AWS using root of trust chip and an OTA software upgrade. So we decided that maybe we're going to develop our own RISC-V that actually has supports the larger memory, which is necessary for various IoT functions like OTA and secure chip integration. So in February of 2022, a decision was made to participate in multi-project wafer 5 that Google offers. And on February 26th, we decided to create a bunch of wish lists. And we find this wish list very important because a lot of times, like Zen, like the beginners has got more perception than experts. And so we have this like initial thoughts very important, because later on you go back and then fix the project and you use this like a wish list. Even though that engineering wise that the wish list hardly means anything, it actually helps later. You can go back to what you initially intended. But anyway, in March 16th, Rocket SoC generation and logic simulation is complete. By the way, we are using this Google's like Google and then DARPA's open road chip design flow. And March 16, we were able to finish the logic simulation. And open logic synthesis job through an error in the middle. And the reason was, obviously, the error was caused by memory deprivation of PC. So we went out to Akihabara and bought 2 Intel Mac Mini and then upgraded it to 64 gigabyte RAM. And in March 19th, open lane synthesis completed somehow.
message shows that the tool consumes 35 gigabytes of memory. Due to the scale of logic, the rocket's SoC generator outputs 200 kbytes of logic, 2 gates of logic, and in an excess of 35 gigabytes of RAM, and in 3 hours were consumed in order to do this logic. An additional iteration was made to address the hold violation, and each took 3 hours. Each run took 3 hours. Open run RAM layout through tons of DLC errors. And then on March 20th, Slack open /open-lane, and then GitHub issued community open.
没声音吗？
对，他在讲话，但没声音。
Sorry, Kawasaki-san. We're having trouble to hear from you. Let me check if I can. I will leave the session for just a minute to rejoin the session to see if we can sort this audio problem. Hi. Hi, can you hear me? Sorry, let me just hang in here. I will be sharing. I will be doing some quick debugging. I can see that your voice is coming in actually, but it's probably from my end. So I will be keep talking, and I will be keep. Let me see if I can do it. Kawasaki-san. I'm thinking that maybe can you use the Skype? I will go another machine to use Skype to talk with her. Hello. Maybe we can use this kind of hybrid solution that the voice will come from the Skype, but you can use the Google Meet to share the presentation. Is that okay with you?
Yeah, that's fine. Great.
Okay. Then we will do it. You can keep on going your slides, please.
Okay. Can you see my slide okay? Hello?
Yeah, I can see your slides okay.
Okay, great. So what happened is, like, we were late for that Google's free shuttle. And, but in March the 27th, finally, after trial and error and a lot of help from like people, we were able to create the GDS2. The design passed the local pre-check and late for that MPW5, so we had to move to MPW6, which is 3 months later. So what happened is we have worked on that, regrouped, and then decided to design. And then decided to write Chisel for like a QPI PS round interface mapped to CPU address space.
So original Sci5 IP can map flash to the CPU address space, but not PSRAM. So we had on May 2nd that we had to pay, get the PSRAM model to simulate the QPI interface. Obtain a model of IoT DRAM, a fancy name for PSRAM with QPI. The model contained encrypted Verilog. So the designer had to move from Icarus Verilog to Model Sim Questa to run simulation. And finally, May 29, leveraging Sci5 E300 chisel code with the original specification. We modified 400 lines of chisel. The engineer only needed to correct the logical description part and then was able to create the SPI interface and map PSRAM to memory. Synthesis and layout was repeated due to the fact that RAM is at the top of 100 lines of Verilog, again had to be manually modified. And in June 2nd, project was modified. So essentially, we use this eFabless Caragol asset, which actually does have a lot of functions to assist you and then create the sandbox. And then we still have many questions, like you probably are very interested in asking questions like Chisel versus Verilog. Like how Chisel performs compared to Verilog, for instance. And also you probably want to ask things like, how does that open source EDA tool chain performs against commercial EDA? And also external memory, power simulation. Can you do power simulation? What are we going to do about MPW7? But anyway, these are many of the questions that we still haven't answered. But anyway, one thing that is good is we can evaluate the chip once it's back. So for every SoC, we need an evaluation plan. The best way to do it is build the chip in the system and give some role. In this specific instance, we gave a current monitoring task to Marmot. Current monitoring, power current monitoring task to Marmot. Once we receive a chip, we build our SoC into the system. And here's that Marmot power supply board that actually has got the 6 power rails and then current measurement output for 6 3.3 volt power rails. And we are able to just actually measure current of the various parts of the system like this. And also, another interesting thing is, particularly like a network Wi-Fi processors, there's no way to check the packets. So the only way that if it is doing okay or if it's not corrupted by malware is to evaluate the power waveform. And then this is the one area that we are working to just actually figure out what we can do with this type of stuff. And this is where where the original data. So like the Caragol GitHub, like the Sci5 E310, and then you have OpenRAM Chipyard, and then there's a bunch of other things. So, okay, I'll summarize the presentation. Essentially, RTOS consumes less power than Linux, so suitable for energy harvesting IoT. And then another thing is, like as in our working, we found out that the root of trust chip integration and secure OTA firmware upgrade takes more memories than we anticipated. And then number 3, measuring chip current is a useful practice. Might be able to detect malware and then hardware implant or cloning of the system. Number 4 is we designed the custom IP to give SoC megabytes of flash and RAM mapped to CPU memory space so that aforementioned memories are actually being supplied. So we leveraged Rocket open source IP, Sky 130 open source PDK, and OpenLane open source EDA tool. And of course, before all that, RISC-V open architecture. So we pretty much, of course, FreeRTOS is also open source. Hence, everything is pretty much open source. And we plan to continue SOC efforts on the MPW7. So I have to acknowledge that this result was obtained as a result of secure open architecture fundamental technology and its AI Edge applied research and development, commissioned by New Energy and Industrial Technology Development Organization. So that's pretty much my presentation. And if you have any question, I should be able to answer.
Thank you very much, Kawasaki-san. Thank you very much. And personally, I have a question that there are many open source RISC-V SoCs and cores. So why did you pick the Rocket E31 instead of others? Is there a particular reason for choosing the E31?
So what happens is like that. It's very rare that E30 310 like G003 is just being productized and being sold as a chip, and then its IP is actually also open source. That's very rare, I think. So one, like all the peripheral functions and then everything seems to be working okay because we have been using this platform for like the last 3 years in addition to like a Andes platform for RISC-V. And then we do know that IPs are reliable. That's the reason that I use that Rocket IP. If that answers the question.
Yeah, that's very clear, and I'm so inspired as well. So I will be asking the people here if they have any questions. Okay, so most of them are, it's kind of hot in Taiwan now, so people are feeling dizzy, and so I will do the asking. I'm quite wondering that do you have encountered any kinds of hiccups on using the OpenLAN because it is still in the early stage of development, and from my understanding that many the analysis and checks from the commercial tools are not supported in OpenLAN. So is there any errors or bugs you have encountered and you think is very worth sharing with us?
So what happens is like, as far as I can see, we didn't even see a single DRC error on standard cell. So on Sky 130 open road, and therefore that the standard cell is very mature, and then all those DRC and LVS is okay, but on the open RAM, I guess that the DRC and LVS is not mature yet. But it is maturing very quickly because nobody has used the huge like RAM before, but in the maybe last half a year, everybody's starting to use huge open RAM. So I think it's going to be okay as time goes on.
I see, and yeah, thanks very much because a bunch of people I know have tried to use Open RAN on their own, and the Open RAN is quite broken for their design. So, thanks for pointing that out. We will be very looking forward to the improvements on Open RAN, and also on the. Let me rephrase it a bit. Will there be a generation 2 of Marmot SoC, or this will be the last one?
Pardon me?
Sorry. Will there be another generation of the Marmite, the SoC you have designed? Will there be a generation 2?
So I guess for us, I think we are planning to just actually run another round or another generation of RISC-V, and then if possible, we would like to do the SH2 too. I mean, open source some of those like IPs that we have been developing for last years. And am I answering your question?
Yeah. Sorry. I was asking a very weird question. So thank you for clearing things up, and I understand clearly. So do we have questions here? No. One last question from my end. I'm curious that because you're in collaboration with the UEC, which is the Denki Daigaku, I think I'm pronouncing it right. So are they trying to engage with the RISC-V community more, or this is just another one-shot program?
No, I think that UEC has been very advanced. It has been doing like a very, how should I say, ambitious plan, like implementation of RISC-V, and in the past, and then separate from us, and then together with us. So they are really into this RISC-V right now. So.
Yeah, thank you very much, and thanks for joining us in such a short notice. I'm very sorry, and I'm very happy to have you here. So I think that will be the end, and arigatou gozaimasu.
Thank you very much for your time.
Yeah, thank you. Bye-bye.
So I'll sign off. Thanks.
我离下一场还有多远？我现在突然有点，这刚刚这实在太超频运作，我现在突然整个进入有点省电模式。3.0，我超时，是已经开始了吗？已经开始了。OK， 好。那其实下一场讲者后来他刚其实我刚刚为什么会这么乱？就是他其实有提醒我说，就是他后来有给我一份预录的，那就直接开始了。就是所以好，那我这边我也就话不多说。
I'm from Croatia, Zagreb, and here I will represent my makerspace Radiona and company Intergalactic. First, I just want to thank organizers for accepting my talk and allowing me longer presentation. I will also want to thank open source community for supporting us from the start. In this presentation, I will talk about open source hardware, especially about the FPGA boards, ULX3S and ULX4M. So let's get started. Just a little bit about me. I spent most of my working time, around 15 years, on repairs, starting from IT equipment and ending on banking equipment repair. So I was quite familiar how devices look like from inside and how components are interconnected. That experience took me to the next level of designing and programming industrial IoT devices, mostly different types of smart meters. After that, me, Deborah and Namir from Radiona opened a company called Intergalactic that is focused on open source solutions. I'm a member of Radiona for around 10 years. It is a really great place for expanding your creativity, to meet people that think on a different way, to hang out or do collaboration projects with others. In Radiona, there is a lot of members from different fields and different skills, like electronics, arts, design. Combining those skills and collaborating, we are creating a really interesting future. As this presentation will be most talk about FPGAs, let me try to oversimplify what FPGA is. So if I have one sentence to describe what FPGA is, I will say something like this. If you can imagine really big number of programmable switches placed inside of devices, by programming those switches to be on or off, you can get any digital logic. And after some time you will spend in writing HDL. HDL is hardware description language. You will notice that it is really similar like putting chips on the breadboard and connecting them with wires. So with HDL, you are not programming like on MCU, you are describing how hardware will look like. And now just a bit of history about ULX3S. ULX3S was developed in 2016 as a need of improvement of ULX2S that was used in Faculty of Electronic Engineering in Zagreb. Davor and Marko agreed on the features every student would need for learning digital logic, and Davor started hardware development. At that time, I was just helping them with some ideas. ULX2S is designed by Marko Zec, is looking like this. Design was not available by an open and production company that did production for university lost designs files at some point. So Marko and Davor agreed that the only solution for a new board is to be open from start, with design files available for everyone. On the ULX3S, they decided to go with the lattice ACP5 FPGA chip. Davor put a lot of effort to make board compatible with different ACP5 sizes. On ULX3S, we can use 12F, 45F, 85F, and with small correction on one power supply, we can also use and UM5G devices. We have discovered that 12F is enough for most of the projects, but most sellable device is still 85F. Second part of ULX3S is SDRAM memory. Maximum memory on ULX3S can have 64 megabytes. But we have only one batch with 64 megabytes. All other batches are 34 megabytes as that is mostly enough. Idea behind SDRAM over DDR memory was some already done projects like Minimig, Oberon, X186 and similar retro projects. At that time, Free FPGA board also had SDRAM, so we wanted to be more compatible. As for the programming, ULX3S can be programmed over US1 USB connector that is connected directly to FTDI chip. For programming, we are mostly using FluidProc, that is fork of Marko Zec's FluidProc, but there are also other tools like OpenFPGA Loader. Beside US1 connector, we also have US2 connector that is directly connected to FPGA pins. We can use that connector for USB bootloader, or we can use it as USB host and have some external devices like keyboard, mouse, or joystick connected. Just in case something goes wrong, board is also programmable over JTAG connector. Along with the JTAG connector, on top of it, there is also OLED connector placeholder. For bigger data, we have SD card. We can use it in SPI mode or 4-bit mode. SD card has shared connections between FPGA and ESP32, so devices can talk with the card, of course, not on the same time. On the board, there are also 8 LEDs. 8 was a great number as we can represent full band. On FPGA designs, LEDs are easy way of debugging some internal signals, so you will always need more LEDs. There is no fancy step-by-step debugging in FPGA, but you can always assign some signals to LED and check what is happening. As for the outputs, we also have GPDI, General Purpose Differential Interface, that we are mostly using for outputting DVI video signals. HDMI monitors are mostly compatible with DVI signaling, so you can get picture on most monitors or televisions. Next connector can be used for audio or video output. For audio, we are using simple 4-bit resistor divider. On the board, we have 7 buttons that are organized like a joystick. So we can play retro games directly on those buttons. Only one button, button 0, has inverted logic, and we are mostly using that button for reset. That button can also be used for powering board on and off, and if one dial is added to the board, we can use that button as multi-boot jump, so we can jump to our next bit stream in Flash. As an input, we also have 4 dip switches, as switches are always useful. Last thing on the top side is a small ADC. It is 12-bit ADC that can have 8 single-ended inputs or 4 differential inputs. Idea behind adding ADC was from Arduino, as users always want to add some external analog devices, or just have few potentiometers. On the bottom side, we have 3 power supplies. We are using Texas Instrument chip that can provide up to 2 amps of current. If we are place UM or UM4G chip, we just need to change one resistor to get 1.2 volts instead of standard 1.2. It can also be used for overclocking. This is just FPGA chip that is used for FPGA programming, but also as a USB to serial interface to FPGA logic. In new version, we have switched to QFN version of the same chip. As FPGA starts, it always starts empty and depending on settings checks for the bit stream. In our case, bit stream can be placed in Flash. We have 64 megabytes of Flash, so sometimes we are also using it for other purposes like holding ROM games. One of special features of the ULX2S is RTC chip that has small memory that can hold alarm. So we can use this setup to have RTC in, for example, Linux, but the design is also made in a way that RTC can provide wake alarm for the board. Board can be powered down, and on alarm it can wake up. While in power down mode, it only consumes 10 microamps. Battery is only to keep RTC time. So you will still need to provide 5 volts for the board. Last thing on the back of the board is ESP32. And as designs of ESP32 changes, we have a footprint design that in that way, so you can hold Vrover or Vrom modules of versions of ESP32. ESP32 arrives with preloaded MicroPython, and combining external MCU and FPGAs gives endless possibilities. One of the cool usage of ESP32 is having OSD overlay on the top of the FPGA picture. So in retro games, we can browse SD card and load game ROM on the fly. ESP32 also gives this board wireless and Bluetooth, so we can connect to external network, or we can use Bluetooth for different things. Once I was using ESP32 to connect to external Bluetooth speaker, so I had FPGA sound core playing sound on external Bluetooth speaker. And here is how current version of the board looks like. A few more things I didn't mention. Oscillator on the board is 25 MHz. This value is not so important, and you can use internal PLL to get almost any clock value. We have 3 more LEDs that are used for serial connection and ESP32 identification. On each side we have 40 pins that are arranged in a way to be PMOD compatible. Out of 56 pins on header, 28 are differential pairs. Small FEN connector is here so we can hold ESP32 in reset, just in case it takes over the SD card. And G5 can be used to switch left bank's voltage to 2.5 volts, or we can provide other smaller external voltages like 1.8 volt if needed. On the top right side of the header, there is also 5 volt input output, so you can provide 5 volt over that connector or use USB and have 5 volt out for external peripheral devices. Just a quick overview of the front side of the board and the back side of the board. Campaign of the ULX board was quite successful, and until now we have sold and delivered around 2,000 boards. Those are real high numbers for a small startup like us. There is so many other things I did not mention about this board, so I will show you a campaign video that is showing a lot of interesting projects that are running on this board. Enjoy 2-minute video while I am having a sip of water. You may have noticed in video that we are mostly using open source toolchain. ULX3S would never be so popular if open tools are not available, so our big thanks goes to Yoshi's HQ team that is making enormous effort in providing open and available toolchain. Thank you, Yoshi's HQ. So after campaign, we could not sell that amount of board over our makerspace. So we have decided to open a company that will handle everything around ULX3S and be focused on new open source hardware software solutions. We named the company Intergalactic. Once board were produced, we needed to have some batch testing. We already have internal tests that was good for checking if board is okay. But when you have 1,000 boards at once, you need some scripting. Dobrica Pavlinušić helped us on this first batch and made our awesome batch script testing. Batch script was great when I was doing it, but once I switched testing to a production company, they were quite lost with those scripts. So I had asked Nbox if they can help us. A month later, I got this fancy GUI tester that any production company can understand. There is a bunch of ULX3S examples out there. So we have created, let's call it startup page, that we are refreshing from time to time to include every project we found. but GitHub is also full of ULX3S goodies. So make sure you check missed examples that are covering all board peripherals. We have also designed a lot of open extensions for the ULX3S, and we are currently selling 3 of them. First is USB extension that gives you 2 additional USB host ports, as for some projects you will need mouse and keyboard, or even joystick. GPDI can be used for additional GPDI output. It can also be used as DVI input. We had samples of getting 640 by 480 input, but it may need a bit more work as timings is not automated, so you need to adjust timings with the buttons to get stable picture. With high resolutions also work, but it is hardest to get timings right, and high resolutions can have more noise. The last extension we are selling is for OV camera. You can use up to 2 extensions of one ULX3S board. Check other extensions on my GitHub account. As for availability of the ULX3S and extension boards, you can check Crowd Supply, Mauser, or NVOX site, or you can contact me directly. I have already mentioned NVOX. They have great open source projects. So at some point we decided to collaborate and combine BB3 measuring equipment with ULX3S. We did manage to do it, but it was painful to combine ESE MCU board and ULX3S, as NVOX boards was done in Eagle, and ULX3S designs are in KiCad. After adding FPGA to NVOX projects, others started to ask the same. So I was thinking, why not make ULX3S modular? So everyone can easily put a connector and have FPGA in the system. ULX3S has too many components for that, and it was too big for integration. So I have asked NLnet Foundation, will they help me making modular version of the board? And they accepted my offer. So they are financing development of 2 modular boards. As making connector fit is not easy, we are also decided to have 3D models first, and NLnet also agreed on financing 3D modeling and experimenting with Blender. All 3D work is done by Paolo Bucher, also a Radiona member. And here are some pictures from the Blender. Paolo also need to use FreeCAD at some point, as there is not easy way of importing geometry into Blender. You can read more about the Blender progress at intergalactic.eu under News, as we are trying to record our progress in a blog. We have tested different connectors, but at the end we got to a conclusion that connector that is used on Raspberry CM4 module is good enough for everything our board will offer. It is also available and cheap. And once we have selected that connector, we got to a conclusion that we can also be pin compatible with CM4 IO. As with compatibility, we will get a big range already existing CM-IO base boards. So our first board was SDRAM, and on V002 we managed to squeeze 2 buttons and 4 LEDs. Additional to ULX3S, ULX4M will all offer usage of SerDes pin and MIPI CSI and DSI. On DDR3 prototype, we managed to add 1 more button and added 4 more LEDs, as they are so important in debugging. Also, this version adds 2 deep switches, and most important, we have added USB connectors, so we can use this board even without baseboard. For that purpose, we will just need to use USB bootloader, as USB pins are connected directly to the FPGA. DDR3 board also had place for the 1 gigabit Ethernet chip. Everything is connected, but we are currently unable to find that chip, so we will need to redesign or wait a bit longer until chip becomes available. In a way, next revision SD-RAM version of the board will also have everything that DDR3 board now has. UX4M is now 6-layer board. There are 3 signal layers, 2 ground planes, and 1 power plane layer. As I already mentioned, boards are fully open, and you can check design at Intergalactic GitHub. As for compatibility, for the moment we have released first version of the board. We are getting and buying lots of already designed IO boards and fixing compatibility issue if they arise. The latest gift we have received is this awesome open hardware tablet that usually holds Raspberry CM4 module, but it can also fit UX4M. Currently, we still do not have any sample of driving big screen, but hopefully at some point we will manage to get something on the screen.
真的要给一个 shout out， 这一台是 QT Pi， 是来自于台湾，原本有一位在 Canonical 服务的员工叫 Pank， 然后后来现在人在那个 QT， 就是做 GY 的那个 QT 的 QT， 那他自己本身很喜欢，业余之前喜欢打造这一些 open source 的东西，包含他自己很喜欢做，他之前还有去接过那个电影道具的制作，有点像那个，我不知道各位有没有看那个，有一终结者有一个那个最近过世的那位那个。就很像那种感觉。那其中这台 QT Pi 是他打造，然后我当个中间桥梁，把这一台寄给这个在克罗埃西亚的，就是讲者。然后克罗埃西亚的讲者地址超短的，我跟 Pank 两个来看一下，觉得这会不会他给错？然后然后那位讲者就是这位 Goran， 他的克罗埃西亚就说哦。没有啦，我们这边其实还蛮乡下的，所以没几号，对。然后我就觉得，我真的不好意思，我就对。
open source FPGA tablet. The goal of having completely down to last transistor open Linux with frame buffer is now achieved. Check out how DDR3 is good in Linux on Linux.
他这个是尝试，就是因为他那是 FPGA 版，就要把它接到他就我们那台上面，然后 HDMI 打出来。他说因为那个 screen 是走那个 DSI， 他 DSI 没有 open source 的那个就 display 的 IP， 所以他就先打 HDMI 出来到外面，这样，这是他这部分的。
So I'm just mounting the SD card, and I am just copying picture to memory, and I'm sending this picture to frame buffer. And here we go.
他从那个 GDI 打出来这样。
DDR3 version also have enough memory to run simple X system. And for the end, yes, it can also run Doom. Thank you. So if you need something, you can contact me on the Jitter or Discord. You can follow up Radiona or Intergalactic EU on the Twitter. And yes, you can send me mail or warp@intergalactic.eu. And thank you.
好，基本上就是这位讲者是一个很有，我发现因为就最后一场，让我稍微打赛一下。这位是其实我还在念大学吧，大4那年的时候，他如果他讲他是克罗埃西亚的首府的那个叫萨格列布大学，那他们其实是一个有点类似像算社团这一类的感觉，就是一群其实，因为其实不像台湾人，其实这种就是很多你18岁上个大学这件事情其实很稀松平常，可是其实很多国家其实他们上大学这件事情其实非常非常耗费。所费不赀的，他可能要去外面工作几年，或者念书。对，所以他们其实这些虽然讲就是学生社团，可是年纪都不见得比我们就是18岁，他们有些可能30几岁去念大学这样。对，那他们在念大学的时候就觉得，因为像台湾这种，你可以很轻易的说上网，然后什么eBay，然后 FPGA 就买过来，这其实是很在国外，尤其是东欧国家看起来就觉得很莫名其妙的事。在东欧国家，他们那个其实你像最近就在打仗嘛，就是那其实是一个。因为其实资源不丰，他们就会想说，那我自己能不能自己做个 FPGA 开发版， 然后而且他们也不见得有经费可以去买 Xilinx 的。那个时候那个年代 Xilinx 还没有 Webpack， 那个年代 Xilinx 啊，然后 Terra 这种都是要配的那个 EDA 拖券，所以他们找了open source EDA 拖券，然后自己去勒 PCB 板，然后最后做了一张 FPGA 开发出来。然后那时候我还在念大学，我就写信跟他讲说，我觉得好有趣，我想要玩一张。然后那时候还没有，那时候 PayPal 好像他的国家很麻烦，然后最后我还是去银行去办那个 wire transfer， 去把钱给他，就连 PayPal 他都不见得能够收。那种这种千几百块把那张板子搞过来之后，然后就开始也是学，就是因为那时候其实在念大学，那时候的电路，然后就开始在玩一些那个时候还没有 RISC-V， 那时候叫 OpenRISC， 就是另外一种 architecture， 一个很小的 RISC-V， 那其实白算盘有个 DEX 的架构，然后拿去改的叫 OpenRISC 这样，然后那时候开始玩说那个可以布起来，然后可以 porting 这样棒棒这样 anyway。然后后来就他到现在是出到第4代，他刚刚有讲他从 UX 2S， 然后3S 到现在4这样，然后他其实做到第4代的FPGA版，然后也是认识很久的老朋友，所以我刚刚讲说，他后来他刚刚就讲说，我觉得你要挪我时间可以啦，可是我实在后面有事情啊，不然我送我就 video 丢给你自己播这样，所以就变成这样了。就是最后，因为刚刚那位你也各位在座都知道，那个日本讲者那一段那个时代。变动太大，超出了一个常态的 range， 就变成这样了，对。所以蛮有趣的，我就觉得，我最后就做就这个 track 最后的总结，就是我们虽然说我自己本身也是一间 CPU/IP 公司，但其实在业余时间也好，学习时间也好，其实都有很多这种 open hardware 的 track 跟 community， 在台湾可能没有那么红，那就是在国外其实蛮多的。那也就是如果你想玩 open source 的，不管 EDA 是给 FPGA 还是给 ASIC， 今天都听到了。那甚至连 PCB 板它用 TCAD 的。他是在一个就是随时旁边可能都会爆发战争的国家，他去弄一个 PCB 板出来，为了他们自己的就是学习跟就是玩乐也是一部分，然后做这样的东西。其实我觉得台湾人要玩这个也不难，对。那很感谢各位今天陪伴我们这个推到最后，小弟在此一起躬，谢谢。哇，感谢，那我就把直播给切了。